Good morning. Hi, jury members, those of us here with us today in this room, and all of you joining us online. Welcome to the Educational Building Division. Before we proceed, can we have a big round of applause for the finalists? Yeah. Thank you. I mean, so that we can have our bloods pumped up, and it's gonna get colder as we go. Yeah. So educational building divisions hold a unique place in SDI, as students have opportunity to redesign learning spaces for their own generation. Around the world, initiatives like those set at COP26 summit aim to decarbonize schools and integrate sustainability into education. Many of these years' entries align with these global priorities, shaping the future of educational buildings in India. I'm excited to welcome you all to the presentation in the Educational Building Division to find out how these teams are future-proofing educational building divisions in India. My name is Manish Kumar Konsam, and I'm the MC for today. It's my job to keep us on time, and I'll be taking this very seriously. Our finalist teams have put in a lot of work. They've submitted their projects and reports about a month ago. And today, these teams will present their work to the jury. Teams, you will have 30 minutes to present your presentation, followed by a 10 minutes Q&A session. There will be a 5-minute breaks after that. You must use those 5 minutes to take your component model out of the room and allow the next team to move their model in. The educational building division has 3 jury members. See you again. Yeah. These jury members have had 3 weeks to review the report submitted by the teams. They have looked at your work in detail and have already assessed your entries for the 10 contests for the decathlon. Teams, your presentation will help them hear your narrative. They will assess your presentation and mastery over your solution through Q&A session. They may revise the scores based on what they hear from you today. Jury members, I'm so excited to have you meet the teams today, finally. But I will need to interrupt you time to time during the Q&A session, so please bear with me. And keep your comments and questions short and to the point. So I think we're ready to begin. So let's start with the presentations. Okay, so our first presentation is from Team Nirman. They have worked in Project Astitva in Sakri Dhule, Maharashtra. The team reimagines the Eklavya Model Residential School, making it culturally rooted, sustainable, and affordable learning environment. Okay, so I request the team to come up to the stage and open up their presentation. Okay, so teams, you will have 20 minutes to present your work to the jury, and at 15-minute marks, I'll be ringing this bell. You will have the first 20, you will have a 21st minute, which means at 20 minutes, I'll ring another bell like this. And if you don't stop, I'll keep ringing it. So by that, I'll ask you to end your presentation. After that, you will have 10 minutes of Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. Good luck.
Hello. India has over 100 million tribal citizens, yet nearly half of tribal children drop out before finishing school. With a literacy rate of just 59%, far below the national average, the gap is clear. But the issue isn't just access, it's belonging. Tribal students often study in schools that are poorly lit, uncomfortable, with poor sanitation, and disconnected from their way of life. And when infrastructure is good, it often comes at a higher cost. Namaste, we are Team Nirman, and today we are excited to introduce our project Astitva, a net zero Eklavya residential school. I am Paranjay. I'm the team lead of a multidisciplinary team of 14 students of architecture, civil engineering, and interior design from MSAP and MIT, guided by our faculty lead and advisors. Our project partner, NEST, under the Ministry of Tribal Affairs, provided us with key requirements, one of them being adhering to the EMRS guidelines. Our industry partners and experts guided us in developing solutions for our project. Our site is located in Sakri, in the Dhule district of Maharashtra, where over half of the population belongs to the scheduled tribes. Our site is part of a larger campus with upcoming accommodations and staff facilities surrounded by agricultural land. The climate is classified as hot and dry, and the thermal comfort ranges from 22 to 30 degrees as per IMAC. Our site spans approximately 5 acres, 45 square meters. The school is designed for 480 students from grades 6 to 12, along with 47 staff members, which adds up to 527 users. Our narrative is rooted in the idea of a tree. The roots, it represents the tribal culture, farming, and vernacular design, often overlooked in typical schools. The trunk, it reflects the current EMRS program with over 477 schools serving nearly 1.4 lakh students. But it's the branches where we see potential. Many schools still lack comfort, sanitation, and inclusivity. Through Project Astitva, we grow these branches into outdoor learning spaces, innovation labs, and community-led education. The site was zoned based on the program, guided by shoebox modeling and climate data. The build form responds to natural slope, minimizing cut and fill, and is arranged in clusters to optimize wind flow. Inspired by tribal village patterns, blocks are organized around courtyards that create microclimate and foster informal learning and gathering. Every design move, from orientation to massing, was shaped by sun path, wind, and topography to create a climate-responsive, culturally rooted school environment. Here you can see clusters of classrooms and labs supplemented by co-curricular, admin, and sports facilities. Open learning spaces in the form of kund, learning pods, and courtyard foster holistic development and also act as community gathering space. A seamless blend of built and unbuilt to create a sense of place. The master plan, it responds to both site and climate with the following design strategies being implemented. As you can see that there's a focal point and the entry for the students is from the west side. The admin and the library blocks, the classrooms blocks are staggered to enhance natural ventilation and daylight. The admin and the library blocks are placed near the entrance for easy access. This is a classroom cluster featuring clerestory with alternate louvers and glazing to provide stack effect and enhance natural daylighting. We have provided green pockets in cluster as social nodes. Together, these elements create a learning space that's not just functional, but deeply rooted in comfort, culture, and context. And here's how it comes to life. While keeping the design in mind, we have thoughtfully integrated site services.
Our engineering and operations approach is rooted in structural and material optimization, waste diversion, and integrated system performance. Through a manual closed-loop solid waste system, over 90% of our 73 kg daily waste is diverted from being sent to landfills and incinerators via composting, recycling, reuse, through community workshops on paper and plastic upcycling. A dual pit setup yields compost every 42 days for on-site farming, and residual waste is stored in a 7-day storage capacity pit before collection. We have provided a 2-stage evaporative system as per functional and project partner requirement. It cuts down the peak load to 57% and utilizes only 6.7% of our total water consumption, achieving a cooling efficiency of 396 square feet per tonnage, which makes it a low-cost and low-maintenance solution. To streamline energy use, our system combines solar battery and smart net metering to respond to grid stress by shifting non-critical loads to low-tariff hours. By implementing GB strategies like shape, shift, and shed, we align demand with solar availability and reduce peak load. We also involve students via implementing interactive energy dashboards to increase awareness. After intensive analysis of multiple structural iterations, we formulated a composite load-bearing structure. The foundation system uses trapezoidal masonry strip footing which distributes the load uniformly, while our wall system is designed with CSCB and Flemish bond below plinth and above lintel for structural strength, and Latra bonds with jute fiber and epoxy in cavity to improve thermal insulation, reduce material usage, and prevent moisture ingress. Our innovative CSCB Marty blocks, for which we have a component model, was made in collaboration with Green Gems and Nirmiti Kendra. Instead of cement, we have used binder, which is made up of 90% upcycled materials, zero clinker, and has low water demand. According to the tests conducted, these blocks are now classified as Class A bricks and have a carbon footprint reduction of 85%. These are thermally efficient and can be made on-site using suitable local soil. For our roof system, we have developed Malvar Plus roofing system, which is an innovative take on the traditional Malvar roofing. Instead of mud, we have used rice husk, which reduces the roof weight by 65% and enhances thermal performance. It uses 100% local materials and requires no specialized labor, making it ideal for easy implementation. We have also developed a built-up triangular truss system in collaboration with structural engineers and Nirmiti Kendra. It uses angled sections and 12 mm rebars. It can be fabricated on-site and achieves longer spans while using less materials. Additionally, it saves up to Rs 23,000 per beam and is compliant with IS 800 code. We have included interactive tools for environmental education like bioagriculture and rainwater chains, which offer hands-on exposure to conservation practices that the students can take home, impacting the community directly. The outdoor gym doubles as an energy learning tool, converting kinetic energy to electrical energy for fans in interactive spaces. If our campus is designed to be accessible to all, why should physical well-being be an exception? Our push and pull universally accessible seesaw was co-designed with product designers and engineers. It features a foldable ramp, locking system, and anchored handles. It also has a provision for non-wheelchair users to engage, making it truly inclusive to everyone. Designed to cost only Rs 18,000. It uses simple and recycled materials, and it comes with a full replication manual as well. Every element of our project was co-created through close collaboration with designers, architects, engineers, material experts, and industry partners working side by side from concept to execution. From passive strategies to structural systems, from our Marty block to our seesaw, every decision was shaped collectively. To enable adoption, we have prototype manuals which we'll be sharing with NGOs, nests, and other government bodies. Over to Anjali.
Moving to building performance, a comprehensive pre-design analysis indicated that the true north-south orientation resulted in good thermal performance. But to enhance airflow and ventilation, a 45-degree tilt was adopted. A staggered layout with this orientation was finalized to optimize daylight and ventilation. From our base case, we derived a target EPI of 32.49 kilowatt-hour per meter square year according to Super ECBC standards. Orientation-specific overhangs were designed, which became a part of our first ECM, which resulted in a 4.02% reduction in EPI. We have iterated multiple options for building envelope. For wall, the final U value achieved was 0.305 watt per meter square Kelvin. The final roof composition achieved a U value of 0.434 watt per meter square Kelvin. Use of efficient glazing types based on function allowed an overall envelope optimization with a reduction of 4.06% in EPI. Furthermore, implementing other mass construction. Meanwhile, shaded walkways and overhangs minimize heat gain and reduce thermal shock. We compared the operative temperature and outdoor DBT to show that there's a significant reduction in our indoor air temperature. IMAC range of comfort is achieved both in naturally ventilated as well as mixed mode methods. North side windows maximize daylight and ventilation with clear story and glass windows, whereas the south facade has smaller shaded windows to limit heat gain. Windows opposite the blackboard are equipped with Natura Advantage by Asahi Glass, which reduces VLT and SHGC, which in turn reduces glare. Additionally, we've also provided bamboo chillman blinds that enhance the visual comfort in classrooms. To combat Dhule's air quality, our school is surrounded with dense vegetation and shared gardens, which act as a barrier to pollutants. Also, additionally, we have used low VOC paints and finishes and lime plaster that absorbs pollutants. Social and mental well-being is also promoted through spaces like learning pods and an open gym facility. Moving on to water performance. We have achieved a 54% reduction in domestic used water, bringing down the water consumption to 20.69 LPCD. We have arrived at a total of 1.7 liters per meter square for irrigation use by using local plants like neem and polash, and 33.7 liters per ton of cooling for a two-stage evaporative cooling. Major key water strategies that we have used are rainwater harvesting, use of earth focus aerators, dual and low flow fixtures by Jaguar, waterless urinals by Ecom Eco, permeable pavers and dug wells for groundwater recharge, and recycling of wastewater. Drinking water is supplied by the Jal Jeevan mission, whereas other potable needs are sufficed by the harvested rainwater. Non-potable and irrigation needs are sufficed by recycled wastewater. We have used burn brick pavers to facilitate groundwater recharge in our hardscape. And we've also designed a bamboo charcoal filtration process, which is a natural filtration method for our rainwater. All water-related services have been zoned based on access and highlighting water bodies, swales, dug wells, rainwater filtration, STP. To conclude, we are achieving a net positive water status by returning back 6 times more water than taken from the Jal Jeevan mission. Dhule faces 2 major risks, heat wave and drought. For heat wave, high thermal mass construction, courtyards, vegetation, and a foldable fabric roof for open spaces. For drought, we're taking measures like practicing rainwater harvesting, low flow fixtures, and replenishing the groundwater table. We have also provided a 150 mm lintel band for earthquake and a power backup in times of power outages. A clear fire safety plan along with SOPs have been put in place. We aim to help the community by providing gathering spaces, employment opportunities during the construction process, and awareness about government schemes and medical camps. Over to Tejas.
Our approach to optimizing embodied carbon emissions involved on-site material procurement, minimizing transport emissions, implementing carbon sequestration, and composting on-site. Furthermore, we designed our envelope systems to optimize carbon emissions as well. This resulted in a 72.6% reduction in emissions, the largest seen in fenestrations, walls, and structural systems. To minimize transport emissions, we have ensured 85.6% of our materials are procured within a 60-kilometer radius. These materials are durable and easy to maintain. With on-site carbon sequestration, we offset 791 kg CO2 equivalent of carbon. We further analyzed construction and manufacturing emissions using one-click LCA. This demonstrated that we achieved a high benchmark of 118 kg CO2 equivalent for cradle to gate emissions. The analysis of the following use and end-of-life stages also showed promising results. We have ensured 97.5% of our materials go from cradle to cradle. A green building usually comes at a steep cost. However, Astitva is proposed at a cost of 2,234 rupees per square meter, a 27.4% reduction from our baseline. This was possible through quantity and load optimization, right sizing of structural systems, and the extensive use of local materials. While we have seen reductions in most systems, MEP services are significantly higher than our baseline due to the use of efficient fixtures. This, however, has helped us in reducing utility costs by 76.5%. Moreover, reductions in building maintenance and HVAC running costs brought down operational expenditure by 60.4%. Supplemented with our solar PV system, we have achieved a payback period of 14 months. This project is proposed to be completed in 54 weeks, i.e. 13 months, where each activity is scheduled to minimize delays and ensure efficient resource use, thus preventing cost overruns. What does this mean for the stakeholders? To the primary users, we provide a school that is safe, inviting, and familiar with smart, modern, and productive classrooms. Open learning spaces and connectivity with nature facilitate mental well-being. By taking inclusivity beyond buildings, we ensure everyone can grow holistically. To the community, we provide employment opportunities during construction and operations of the school. We've also provided access to social infrastructure, skill development facilities, and facilitate awareness programs on various government schemes. The school also helps improve literacy rates in the region. To our project partners, we have provided a context-driven net zero EMRS with replicable solutions. This model ensures Astitva is an affordable and certifiable EMRS. We have ensured significant savings in energy use, carbon emissions, and water consumption and project cost. What next? Over the next 5 years, NEST has sanctioned 100 EMRS across India. With our replicable solutions and ready reckoner on context-driven design guidelines, we ensure data-driven design and funding for the EMRS initiative. Furthermore, we look to ensure 90% transition rates to higher education, especially for girls, to uplift over 1 lakh students, thereby strengthening NEST's mission. We also look to facilitate training and employment of the locals to help sustain their livelihoods. Astitva is not just a school. It's a sustainable, replicable model that redefines education for India's tribal students. Thank you.
Thank you, team. You have 3 minutes more, but yeah, thank you for finishing well before time. Let's hear from the jury and take questions from them. Samit, I'll start with you.
Better now? I think an excellent presentation. You really packaged it very, very well. It's very smooth and very well integrated presentation. Just a couple of observations, and I think I was just seeing in one of the slides, I think 26 or 25, you propose an evaporative cooling system. You've shown the equipment you have in mind. Could you go back to 25 or 26? Yeah, I think 25. Yeah. So you see, you have an evaporative cooling system in mind, and I'm just drawing your attention to small details which, in real practice, also you'll have to sort of keep in mind. I'm not trying to find out gaps in your work. So the evaporative cooling system which you have, you kept it on a flat roof, to blow up through the flat roof, but all your roofs are actually sloping roofs. You can see all your classrooms are sloping roofs. We've made that with an intention. So this is going to be one of the challenges. How do you integrate an idea into the architecture, And the idea is good. You want to do evaporative cooling. You've done all the analysis. You show that it's going to work. But if it is not built into the architecture, it's not going to work in real practice as well. So some small, I would sort of encourage you to sort of put some attention on that. And if you see these components, and you try to figure out how you're going to serve each classroom with this, I think that will automatically start forcing you to make some changes to your architecture. Small advice, but I think excellent presentation. Otherwise, just a little more detail probably would have been excellent. But very good. Thank you so much.
Elise, would like to hear from you.
Please.
Yeah.
Thank you. Thank you for the presentation. Super clear work. I would say great thank you for the clarity also of the presentation and the amazing graphical work. It's really easy for me to follow and to understand. I have a question on the comfort and the way you want to operate the building. So you showed a bit like how you want to naturally ventilate, like do the natural ventilation and also having evaporative cooling and so on. But then how do you change that according to the season? Do you operate the building the exact same ways always? Or do you have a seasonal operation of the building?
So the naturally ventilated spaces remain natural ventilation throughout, and using the thermal mass and of our structure, it ensures that we keep comfort even during winter months when it is cold. For the mixed mode spaces where we have evaporative cooling, it is integrated with our GEB to ensure that only when it goes above a certain point, it is operative, and it remains inoperative during periods where it is achieving comfort otherwise.
Thank you.
Thank you. Again, I echo my colleague's opinion that excellent presentation, great graphics, good narration. So congratulations. Everything is tied well, very well actually. Right? I found your design to be really culturally sensitive. Choice of materials, details, all are excellent. It really shows the value of a multidisciplinary team. I think your team has really nailed that. So congratulations. Uh, my question, and I was having trouble understand.
Can you have your mic close?
Okay. The I was having trouble even understanding in your report is about daylight and thermal comfort. Right? So your classrooms don't have evaporative cooling, right? It's only naturally ventilated. So can you show us something where you have done some comfort calculations for the classroom, like a day profile or something? Can you yeah, temperature during the day? Now here you are showing this is average temperature, right? No,
Yeah.
go back. So you have yeah. Here, so is the line which is within the IMAC band? Is it the average temperature during that day?
So this is an annual chart to show that
Okay.
we have achieved comfort across the year. The previous slide
This is for classroom specifically.
yes. So this is for naturally ventilated spaces and mixed mode spaces as a larger thing. The previous slide shows the daily profile of comfort temperature mapped to outdoor dry bulb temperature as well.
So say in July you have 60 of the 160 hours which are not comfortable.
Yes.
Okay. And this 180 is like total 24/7 or it's the occupied hour?
Occupied.
So 180 out of 180 occupied hours, 60 hours are not comfortable. Okay. So yeah, I had that question. So thank you. The second question is about daylight, and you have a very nice axonometric which shows the north light, right? But how many of the classrooms are following that orientation? Yeah, so this is a nice, I like this section, the way daylight is coming. But how many classrooms are following this orientation? Can you go to the site plan? Yeah, any site plan. Yeah. Hmm. Yes.
So here, if you see that all the classrooms are clustered as it is marked as number 2. So they are. So these are the So these are the classroom spaces.
I
And
can't see from here. So can you just tell me which classrooms are facing the north?
so basically our clear story.
Hmm.
So they either face northeast or northwest. So all of the classrooms are getting daylight.
Okay.
You
Are
can use
getting the diffuse daylight.
pointer.
Okay.
Yeah.
Yeah, just highlight the classrooms and that will be nice. Yeah, you can just go and point it out.
Yeah.
So, okay. Cluster is a classroom. Yeah. Okay.
So we have four. So actually we have four different orientations for the classrooms, because it is some are facing northeast, but all the clear stories have been designed so that they get the natural daylight.
Thank you. Thank you. Overall, I found like really scalable solution. So really congratulations. Thank you.
We have some more time. Submit, or at least you want to add something. Yeah.
Yeah, I just had one more comment in the innovation section. If you could go to, I think there were some ideas there. I don't know which page number. So there was a wall which had, I think, yeah, hydroponic bamboo farming on walls. I think this is an idea, but it's not anywhere there on any of this. So I think what we're looking for in this section are actually ideas, innovations which are built into the design. No, these are good ideas, of course, right? But that's what we're trying to look for, as a jury, or that's probably the contest requirement. Something for you to work on, like the mycelium-based growing panels on wall. I don't think
Yeah,
we've
I
seen it
think
anywhere
I
else.
agree on it being detailed out more in terms of it integrating nicely with the design.
Yeah.
But we have proposed it as an educational tool for them to learn about environmental conservation and how they can incorporate these practices in their community. So I mean, I agree it's something that should be detailed out
Yeah,
more. Yeah,
absolutely.
definitely.
Yeah.
Also, if we can just respond to the previous comment also that you had made about the sloping roof
Yeah.
systems.
Yeah.
So the evaporative cooling systems we have provided
Yeah.
are not provided for the classrooms.
Okay.
And there is one that is provided on a sloping roof, and the design we have chosen for that one is designed for a sloping roof.
Okay, so you're saying the classrooms are going to be comfortable throughout the year,
Through
irrespective of anything, and that's a very hot place. We're doing it. Yeah, I hope the data is right.
So, so
Yeah, in occupied hours, 1/3 is not comfortable. So it's something which you need to really worry about, right? I mean, it's 1/3 of occupied hours which are not comfortable. So maybe it's something for you to think about. All right.
thank you.
Yeah.
I also have a very last comment. I think when I was reading your report, you also wrote that you were implementing a night cooling strategy, so with the ventilation, like night flushing the classrooms. How do you put that into place? Because like everything will be open in terms of security, and also like if it's raining or whatever, do you intend to like have it automated or everything manual, or what are your plans?
So the Clear Story has an alternating glazing and louver system. So we are using that for our night flush strategy. So that's why we've intentionally had alternating glazing and louver system so that the hot air can get out from the louvers in the Clear Story.
Okay, so automation you have for the night flushing.
Yeah, so thank you, jury members. Thank you, Team Nirman. A big round of applause for them. Yeah. So let's take 5 minutes to get ready for the next presentation. You can move your component model outside. Uh, our second presentation is from Team Samavet. They've worked on project Swarnim in Yerwada, Pune. Uh, their rehabilitation center for sex workers and women empowerment uh, is a building that act as a uh, vocational building, and they have coupled their innovative shading devices and materials to achieve their net zero target. Teams, you can open your presentation. Yeah, 1 second. So teams, you will have 20 minutes to present your work to the jury. At 15-minute marks, I will ring this bell. You will have a 21st minute, which means at 20 minutes, I'll ask you to stop the presentation. After that, you'll have a 10-minute Q&A session. So keep your answers direct and to the point. Okay, team, the stage is yours. Good luck.
Hello. Hello, hello. Check. Hello. Hello, hello. Check, check. Hello, hello. A very good morning to one and all present here, jury members, other professionals, and my fellow. Uh, a very good morning to one and all present here, and we are Team Samavet, and we are proud to present our project Swarnim in the education building division.
What do you feel after looking at this image?
Is she a rape victim? Is it about domestic abuse?
No, it is about sex workers. India is home to an estimated 8 lakh sex workers enduring exploitation, violence, and social exclusion daily. One such place in Pune is Budwarpet, India's third largest red light area, trapping generations of women in cycle of poverty and stigma with limited rehabilitation opportunities. We, Team Samavet, are proposing a vocational training institute, Swarnim, for sex workers.
I have a suggestion. How about we stop calling them sex workers and start calling them Sakhis?
Vocational training in India has gained formal status through progressive national frameworks like the NEP 2020. These initiatives aim to integrate skill development into mainstream education. We analyzed curriculum preferences and data highlights a clear demand for practical skills. These are the top choices preferred by the Sakhis. This structured modular approach supports NEP's 2020 School of Flexible Employability Oriented Education.
Site for our project is located at Yerwada, which is 7 kilometers away from Budwarpet. This location offers the rehabilitated Sakhis a tranquil yet connected environment for their education. The site has a total area of 30,000 square meters with a gradual slope of 1:20. Climate analysis indicates a warm and humid climatic zone with an annual average wind speed of 1.1 meter per second due west. Our team conducted sunpath, wind, and psychometric analysis to determine optimum orientation and position of the blocks on the site.
Our initial step was to understand the functional needs of the Sakhis. The zoning diagram reflects the relationship-based layout, grouping spaces according to intersections and accessibility. We translated conceptual zones into massing blocks, creating buffer spaces and courtyards. The existing hydrology stream became a key design factor, splitting the mass organically and allowing the ecological interactions. To enhance the passive designs, the mass was then rotated 45 degrees according to the predominant wind directions, improving cross ventilation. Blocks are then staggered to avoid wind shadow and allow natural daylight. The campus's construction unfolds in three distinct phases, mirroring the emotional and social rehabilitation journey of the Sakhis. For the first phase, stone is used. Stone's raw strength and enduring nature represents the Sakhi's firm foundation. We also then began planting bamboo in the first phase. In the second phase, rammed earth marks transition and reflection, mold and shaped. It mirrors the healing and transformation. We then also introduced buffer spaces and courtyards for the gradual exposure of the Sakhis. For the third phase, brick is used as a symbol of self-reliance and reintegration. The matured bamboo in the phase 1 is then harvested and repurposed in furniture and partition walls, rooting designed to self-reliance and circularity. To complement this phase journey, we propose a urban street as a bridge between campus and the city. These streets may host weekly exhibitions of their work. There is also a cafe run by Sakhis which will employ them and enhance the interactions. There is also an auditorium that generates revenue, offering them a platform for expression. More than just a public space, this street becomes a stage for transformation, promoting inclusivity and dignity.
The architectural design features a sensory garden that encourages emotional healing through immersive multisensory experiences. Sight. Sight is engaged through earthy materials and plants. Sound by flowing water. Touch through varied textures and smell by fragrant flowers. This layering nurtures a mindful connection between people and their environment. Our material strategy emphasizes local sourcing and innovation. Bamboo planted in stage 1, harvested later for partitions. Clay from site for rammed earth, cutting transport emissions for used for walls. And mycelium, an innovative material used as compostable acoustic panels for sustainable heat insulation.
The explorative view details the construction of assembly unit. We maximize natural sourced materials like glulam louvers and timber window frames. The unit design integrates natural light and ventilation through north light windows, louvers, fence, and stack ventilation.
So the team approached health and well-being through three lenses, them being physical, mental, and social. The physical well-being was focused using natural ventilation, uh, shaded passages, and meditative spaces. The mental well-being is enhanced through a sensory trail, offering calming, multisensory experiences through biophilic design. And the social well-being, we introduced shared community spaces like the urban street and the cafe, encouraging interaction and inclusion. For further detailing out the health and well-being, the team conducted indoor air quality and thermal simulations. Our ACH simulations show a value between 300 to 450 seconds. According to ASHRAE 62.5, the value standard would be 600 seconds. So the value is under 600 seconds, confirming good ventilation. Indoor wind velocity along with the ceiling fan ranges from 0.01 to 0.78 meter per second. ASHRAE 55 standards recommends 0.2 to 0.8 meter per second, ensuring comfort and supporting passive cooling. Daylighting performance is also covered using ASE and SDI analysis. ASE analysis confirms that the most zones receive direct sunlight for less than 10% of occupied hours, annually minimizing glaze, north ventilation, and pins for shading. SDA analysis indicates 75 to 100% of occupied space receives at least 300 lux for over 75% of the year, reducing the need for artificial lighting. Our building performs well in visual comfort as well as energy efficiency. We also evaluated thermal comfort through adaptive comfort simulations. The design case shows a significant reduction in the discomfort hours. On the PMV versus PPD graph, we considered a critical instance in the month of April, where the PMV value was calculated as plus 0.44 and the PPD value was calculated 9.09%. According to ASHRAE 55, the PMV should range from minus 0.5 to plus 0.5 and the PPD should be under 10%. Our design meets both the standards, confirming its thermal comfort.
For sun shading, the team has designed a dynamic shading system consisting of glulam louvers attached to a sliding track powered by servo motors and linear actuators controlled via microcontroller like Arduino.
The diagram indicates how our sunshade responds to the how a sunshade responds to the sun. It blocks the high altitude summer suns while still giving the access to the lower altitude winter suns. The Arduino and microcontrollers receive the solar data, activating the motors for automatic dynamic shading. Lures respond to the solar movement by rotating and sliding horizontally to reduce heat gain while
Teams,
maintaining daylight.
please keep the mic close.
Yeah. So, all the sun shades are controlled by central microcontroller which is preset to provide optimum shading. So we decided it would be in three particular presets for three different time zones, three different climate conditions. This system was designed for south and west facade. The shading system enhances occupant comfort and significantly improves the energy efficiency. Coming to the energy performance of the building, our design integrates optimized window wall ratios, overhangs, and building orientation. We also employed different ECMs and optimized HVAC envelopes to ensure EPI score of 41.5 kilowatt hours per meter square per year. Our energy infrastructures merges solar film array with water battery system, which is PSH. During the day, solar panels power the entire campus. At night or during high demand, water flows back to generate electricity. This system includes a 4-day backup, ensuring reliability and resilience. Our roof design uses a Kirigami solar film module, which we have made a component model. Out of the 1334 square meter of roof space available, we utilize just 480 square meter for 80 modules. This generate 1,35,000 and 440 kilowatt hours annually, more than twice our annual consumption, which is 61,164 kilowatt hours. The relation of renewable versus generated electricity graphs shows that we are in energy surplus even when we are in the critical months.
Kirigami is an ancient Japanese paper cutting technique. The form used can significantly boost solar efficiency, especially at low sun angles, with up to 40% more output than flat panels. However, scaling and material limitations held it back. So we redesigned the form to match commercially available solar films and fabricated it using CNC milled ABS plastic. The geometry is responsive. One side tracks the morning sun and the other the evening, capturing energy more effectively. What we found most interesting, it's not the surface area, but the number of modules that drives performance, making the system easily scalable and modular. This was all about energy performance. Now coming to water performance. Our water strategy integrates multiple sources to ensure sustainability. Municipal water supply, that is from PMC for potable water needs, rainwater harvesting for non-potable water needs, grey water recycling from washing, and black water treated on site via phytorite system. All treated wastewater is reused for flushing, landscaping, and irrigation. As shown, all water flows are managed for zero discharge in a closed loop. According to NBC guidelines of 45 liters per capita per day for institutional building, we have strategically used low flow fixtures like sensor faucets, low flush urinals, and water closets for achieving a 35.5% reduction in water demand by lowering the baseline water demand to 29 liters per day per person. For rainwater harvesting, we have harvested 8,748 kiloliters of rainwater annually by effective catchment area of 8,957 square meters. This water is directed to storage tanks for non-potable uses. Since the site is near a river, we avoid groundwater recharge to prevent upthrust pressure. Instead, surplus stormwater and rainwater are directed to natural treated landscape like wetland and biospheres. By integrating these green infrastructure system, we have managed water sustainably, improving ecological resilience and enhance the visual and environmental quality of the site. For on-site wastewater treatment, we have used phytorite treatment plant, which is a patent Indian treatment system by CSIR and sand filter grey water treatment. By integrating both systems, we ensure on-site water reuse, minimizing freshwater consumption and aligning with our zero discharge objective. UGWT capacity of 10,150 liters is provided for daily water requirements. Rainwater harvesting tank is sized for 6,29,300 liters to cover irrigation throughout the dry seasons. A fire tank capacity as per NBC norm is given of capacity of 50 kiloliters for building under 10,000 square meter built up area. Additionally, surplus harvested rainwater is diverted into hydro reservoir for the water batteries.
So what is a water battery? So water battery is our site responsive energy storage solutions. While lithium ion batteries are widely used for their high carbon emissions and long term maintenance, they are less suitable for sustainable projects. Instead, we have started looking at what the site had to offer itself. We found a unique opportunity in our site's natural slope and the abundant water availability that led us to adapt a PSH system, or a pump stored hydropower system. The storage system was designed by calculating how much energy was required to power the street lights on our urban trail. From there, we worked backwards, determining the discharge rate needed for the turbine, designing tank capacities that would support the flow, and finally calculating the refill rate and designing the pump size. The core idea was simple. During the day, the solar energy is abundant and would be pumped to a higher tank. During peak hours, outages, or nighttime, same water flows back down through the turbine, generating power. The table summarizes the technical parameters and annual energy generation which the system would do. The system we calculated had the total efficiency factor of 74% overall.
Waste is segregated on site into 5 categories, that is paper, glass, organic, plastic, and sanitary, essential for effective processing and recycling. On site organic waste is processed in a biodigester, converting it into 3 to 5 meter cube per day of biogas and fertilizer. Byproducts are used on campus for cooking, landscaping, and energy needs. Sanitary waste Sanitary waste is a critical, often overlooked issue. We have addressed this issue using the pad care system. The site generates about around 2,100 pads per month. We use biodegradable sanitary pads, which are collected via pad care bins. The pads are processed outside the site in Pad Care X, the world first sanitary pad recycling machine. Using the Solar Decathlon India's carbon assessment tool, we compared emissions between the baseline and our proposed case. Local and on-site sourcing significantly reduced transportation emissions. Overall, we achieved an 85.72% reduction in embodied carbon. Breaking it down, walls see an 84.67% reduction by using stone, rammed earth, and CACB blocks. Structure sees a 74.8% drop with 25% fly ash and a pillar slab system. In floor, we can observe 42.6% reduction using basalt stone tiles. Fenestration has highest reduction by 105.32% by replacing aluminium sections with timber frames. The only increase was in the roof by 63.61% due to China mosaic for night flushing, which improves thermal performance. A key strategy is the filler slab system, inserting earthen pots in non-structural zones to reduce high carbon concrete volumes.
Another key innovation in materials was mycelium insulation panels. These are sustainable, biodegradable insulation materials made from fungi and agricultural waste. Compared to conventional petrochemical insulation, mycelium panels are fire resistant, non toxic, lightweight, and easy to install, and provide excellent thermal and acoustic insulation.
Our campus is designed to be resilient to service disruption and emergencies on all four fronts. That is for water supply, emergency reserve of 6 lakh 29,300 liters, which will last up to 2 months, is given on site. For electricity, a backup of 385 kilowatt is provided, which will sustain for 4 days. For food supply, emergency provision for 350 people for 4 days is given. For waste management, on-site system manage waste via recycling, composting, and controlled landfill. Emergency safety measures are also catered on site. Wall assembly includes a 450 thick rammed earth wall with a stone plinth and lintel band, ensuring seismic stability and durability. We utilize biofuel for storm water control, and buffer zone mitigates heavy rain or fire events, and also control noise pollution. Resilience is not only physical but also social. Our campus supports rehabilitated Sakis, a community facing trauma, stigma, and relapse risk. By offering education, skill building, and a healthy living environment, we aim to build self sufficiency and long term well being. Coming to affordability, affordability in our design ensures long-term financial resilience through strategic reductions in capex and opex. We have achieved a 41% drop in capex, bringing total construction cost down from 18.46 crores to 10.87 crores. This translates to a per square meter cost reduction from 46,506 to 34,143, where major savings came from civil, internal, and MEP works. Our phased construction prioritizes essential spaces early, enabling partial campus operation and revenue generation while subsequent blocks are built. The revenue model projects 1.43 to 2.06 crores annually, with CSR funding contributing 49% and government schemes 35%. The remaining 16% comes from rentals, sponsorships, and donations, creating a balanced and diversified income stream. For OPEX, we evaluated key components. Electricity cost was not included as our solar panels cover most energy demands. The proposed case offers clear operational advantages. Efficient fixtures like BLDC fans and efficient LEDs reduce energy use and upfront cost. These systems are more durable, lowering long-term replacement frequency. As a result, we achieve nearly a 50% reduction in OPEX, with LCC analysis showing a 30% reduction in CAPEX and 12% in OPEX. We have also adopted cost-effective techniques like stone foundation, reducing structural cost by up to 40%, and locally grown bamboo for interior partition. Together, these strategies ensure our campus is cost-effective, quickly deployable, and economically sustainable.
In summary, Team Samaved presents a design that empowers people through dignified work,
Stores energy sustainably using gravity, not lithium.
Reduces carbon and cost through natural and circular material. We believe architecture must heal, empower, and perform.
Where many campuses think of expanding, Team Samaved envisions the purpose of Swarnim to serve its purpose and gracefully returns to the soil, leaving behind empowered lives and a changed society. Thank you.
Thank you, Tim. Once again, we finished before time. Thank you for that. So let's hear the jury. Elise, we'll go with you first this time.
Perfect. Thank you for the presentation. Very sensitive architecture, and also I really enjoy your holistic approach, like not only speaking about the technique and the comfort, but also the social issues and how you can make it work. So excellent work on that. I really appreciate. I have a comment on your Kirigami PV. I think it's super interesting element that you designed and then that you integrated, but I have the feeling, you know, you have to make it more integrated into your design. You know, here I understand the idea. You want to have to catch more of the sun, but then at the end, you know, you have the efficiency of those panels, which are less than the efficiency of the panel itself compared to like a microcrystalline one. So the thing is, if you want to make also those kind of PV panel integrated well into your building, you have to also have a kind of stronger design, you know, like making it like the only solution for electricity generation. You see what I mean? Because on a longer term, then you have something interesting and that can generate electricity and so on, but then at some point in the project, they will maybe come with something more simple, you know, you have a flat roof, so why not having flat PV, you know, on top of it? So if you want to have that, then the design would might also need to be done in regard to that. I don't know if you have an answer to my concern or question, which is not really well phrased, but why did you choose actually the Kirigami instead of other PV?
So the thought behind selecting Kirigami solar module was like, so the module basically performs, as you mentioned, in case of
Mic closer, please.
Yes, so in case of the flat solar panels, the module has a factor of efficiency factor which is lower than the module of Kirigami. But what we observed was, due to it being exposed to the solar longer, sun rays longer, we can effectively keep it active for a longer period of time, and the module being basically replicable and scalable easily. We can, so as in the energy performance also, we have only used a smaller percentage of area of the roof. So if we are able to scale it, because this particular area was sufficient for 80 Kiriyami modules. So if the module is that scalable, we can also include the larger flat roofs to generate more energy, which makes the campus more energy.
Okay. I also have a question on the thermal comfort, if I can ask another question.
Yeah.
So you showed a graphic with, I think it was slide 28, yes, exactly here. So you have your base case, which is what, like, what is actually the base case you calculate? Like you compare a base case and a design case. So your design is what you have done, but the base case is what is when you have no natural ventilation. Or what's the difference?
So it's basically with like not so few windows are closed and not a lot of like natural ventilation. That was the base case, and then the proposed case was the design case.
And so we see on the graph, like you have this reduction of occupied hour being uncomfortable, but you still have some. Do you have a quantification of that? Do you know how many hours are more comfortable now during the year between those two? No. Okay. Thank you.
Yeah, Saket, saw you writing down a lot of things. Over to you.
Just my bad habit of taking notes. I'm learning a
Yeah.
lot, so thank you for great presentation. I really appreciate your attention to details, as she said, to the social context, to the material and the system context. So a lot of hard work, a lot of attention to details. I like your design sensitivity in terms of the urban street and the sensory garden, so the softer parts which are really important. Right? The focus again on the phasing in terms of what everything is never built at the same time. So I think you factored that in. Uh, I have just one question which is nagging me is, though I like the fact that different phases have different materials and they're kind of responding to the emotional context of the residents over time. But how do they respond to the cost and the carbon and comfort, because clearly one would be hopefully better than the other. So how do you make that trade-off?
Right. So the phasing, concept of phasing was done so that so initially for the stone phase, which was the phase one, the campus would be constructed with the stone and the excavated soil, which was on the side. We contacted our civil engineers, and from there we got to know that only some sand admixtures were required on site for the making of rammed earth. So the same soil will be utilized for manufacturing of rammed earth on the site, which saves us on the cost of getting the rammed earth and the materials required for the rammed earth. Also, during the excavation phase of the rammed earth, the soil which will be excavated that time will be used to make CSEB blocks, which will be used from the same soil basically. And the bamboo plantation is done such that during the first phase construction, the bamboo type selected would be mature enough to harvest at the phase 3, which will be used for the paneling and for
Yeah, Sumit.
Thank you for your effort. Very interesting to see this, and particularly the architectural side, and really well done, very sensitive. Good ideas there as well. Just a couple of things. I don't know how many minutes I have before Manish cuts me off, but so there's this, I think you talked about wetlands to manage your wastewater. Where on the site have you planned the wetland? Probably go up, yeah.
So the wetlands are over here.
Right. So again, my emphasis on detail. It's not there on the drawing. I really encourage you to start thinking. But it's a key element to your water performance, right? So it's something which you should not let the jury or anyone else guessing. It should be there, and probably you should also do some thought on how to integrate that into the building. So just a pointer there. And one other question, if do I have time for one more?
Yeah,
I do.
of course.
Yeah. So there's a section on affordability, and I think if you could go to the slide. something I found very, very dramatic. I think I've also commented on that earlier, but I couldn't figure out what the difference was. No, I don't think they did it. I was hoping they did. No, I was just hoping they would. The next slide, I think. Yeah, the next one, I think. Yeah, so what went wrong here? The base case, see, just the lighting itself is 780,000 in the base case and down to 32,000. So almost entirely the savings is because of lighting changes. So either the base case would have gone wrong or the proposed case is wrong. Something would have gone wrong. I mean, it's almost 90% of the saving between the base case and here. Yeah. Typo issues?
Mike, please.
Yeah.
3,600 lumen LED bulbs were used, so that was the thing. So that the lumen were
So the base case was something else, is it? And almost entirely because of lighting.
Sir, actually, it is a mistake by our side. It is a typo.
All right. Okay. So thanks for a nice presentation. Thank you.
Yeah, still have some time. Any last words or any other questions? You want that?
Maybe one comment I'll just add, the water battery. I think it might be useful for you to do a daily analysis rather. I think you've done an annual analysis, so it looks very different when you're doing it annually because of the very nature of availability of solar power. So I think that's something which you might want to really test out. You know, given that it's something which is very core to your, design idea. And I think you've done only annual analysis there.
Yes, so we have primarily done, as you mentioned, annual analysis.
Mm.
But during our Kirigami analysis, which we did, we found out that even in the months where we don't get a lot of solar exposure, we are still in an energy surplus, which is enough to power the pump. So we were like an annual analysis.
So what kind of EPI did you end up with for this building?
41.5 kilowatt hour.
41.5, and you're looking at 61,000 units or so. Yeah.
Yes.
Yeah, something around that. Very less in my opinion, but maybe you've done it right. All right, thank you.
Okay, yeah. I think we're on time. Thank you, jury members. Yeah. Thank you, Team Samavit. Big round of applause for them.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through.
Welcome back to the presentation for the Educational Building Division. I hope you didn't influence the jury members. Our third presentation is from Team Solark. They worked on project Sri Shai Satya Central Trust School in Bada Bagada, Indore. I hope I didn't mess that up. The team delves into vertical trellis facade design and range of usage of agro waste bricks and bamboo screen, balancing the character and performance of their building. Teams, I request you to come up to the stage and open your presentation. Okay, teams, you will have 20 minutes to present your work to the jury, and at 15-minute marks, again, the ring, you'll hear this bell. So, which means at 20-minute marks, ask you to stop your presentation. After that, we'll have a 10 minutes for a Q&A session. Please keep your answers direct and to the point. Okay, all the best.
Hello. Good morning, everyone, and the esteemed jury. We're Team Solak, and we're proud to present our proposal for the Sri Satya Sai Central Trust School, developed in collaboration with our project partner. The site is located on the outskirts of Indore in Bada Bangarda, a mid-segment locality that is rapidly transforming into an educational and residential hub. It is surrounded by institutions such as an MIMS University, Symbiosis Campus and Hostel, residential townships like Smart City and Sky City, as well as agricultural lands. Climatically, the site lies in a composite zone. This is a CBSE school for 3,000 students and 200 staff, operating from 7:30 a.m. to 5 p.m. and catering to both primary and secondary levels. To ensure efficient land use and minimal ground coverage, the school is planned with a G+4 height, allowing space for integrated landscape and open areas. Our base EPI was derived at 77 kilowatt hour per meter square per year, referencing Uganda Public School in Raipur due to similar climatic conditions. And our target EPI was 34 kilowatt hour per meter square per year based on ECBC benchmarks for educational buildings. Our project partner emphasized the following: maximum open land as the school with a school and a garden concept, prioritizing safety and surveillance, zoning and functional clarity in design, and a strong focus on sports and physical development. The school serves multiple user groups: students, teachers, administrative staff, visiting parents, and the surrounding community.
We studied the dry bulb temperature, relative humidity, and solar radiation on our site, especially focusing on the school timings, considering the ASHRAE comfort model. And we concluded that our site experiences hot and dry summers, warm, humid monsoons, and cold winters. We have dry, hot winds blowing from the west and southwest during summers, hot winds blowing from the west during monsoons, and cold winds from the north and northeast during winters. And through our design, we've tried to tackle the uncomfortable heat, excess humidity, and strong winds. One of the main requirements of the trust was to create separate buildings for the primary and secondary section. But we wanted to make a compact and cohesive structure for better functionality. In this, we maintain the segregation with the primary at the top and the secondary section, and we have common programs connecting the two buildings. The common programs include the admin and the library. The sports complex is nearer to the secondary section since they use it more often. And the longer facade of our structure faces north-south to reduce the heat gain.
and we've placed services such as staircase blocks and washrooms on the east and west to again reduce the heat gain within the classrooms. And we've also placed less frequently used programs such as labs on the upper floors to create a solar buffer for the classrooms below. To make our school more climate responsive, we use passive design strategies and facade treatments. So on the east and west, we have used green facade along with bamboo trellises. In the south, we've used planter facades for the inner courtyards and terracotta jalis to cool down the hot southwest winds. And we've also created vegetation screens on the periphery of our site to block the dust coming in from the surrounding farmlands, and also to block the north winds during winter season. The terrace is used for urban and solar farming, along with a green roof under the solar farming to again reduce the heat gain for the classrooms below. So let me walk you through the structure. Uh, First, we have a grand entrance courtyard, which is the summer courtyard, and the design is such that it's self-shaded, so the students can use it for congregation and dispersal as well. Then moving on, you enter the classrooms through a corridor which has a planter facade. It acts as a double facade and reduces heat gain in the classrooms. We've also created common open spaces on the first floor, which are enclosed and safer for primary students. Then moving on to the class, we have ensured that each classroom has an external facade for natural ambient lighting within it, and we've also placed frosted glass windows as well as ventilators in the corridor to ensure diffuse light as well as cross ventilation. Then the south facing courtyards can also function as outdoor learning spaces for the students during winters, and the terrace is used for urban farming and composting, which is a part of the students curriculum as well. The summer courtyard, as mentioned, is self-shaded and has a variety of trees to keep the temperature cool, so they can use it during breaks. The south-facing facade in the secondary section has balconies with planters, which the children take responsibility of, and the landscaping in the courtyard is done through deciduous trees, which allow the heat into the classrooms during winters. And we've also added water bodies to enable evaporative cooling. The ground and the sports complex is used for outdoor and indoor sports along with performance areas, which can also be used during school festivals. And overall, our landscape design mainly is done to, like, we've ensured that each outdoor space has its own unique character to enable ease of navigation for the students, especially the younger ones. And 60% of our terrace is used for solar farming. The section shows the transition of spaces where we have the winter courtyard overlooking the grounds, the self-shaded summer courtyards, and the aroma garden as the enclosed open spaces for the primary students, the terrace in the north. Through this, we wanted to create social common spaces between students of all classes to create visual connections and more social interactions between them.
Moving on to engineering and operations, for the structural system, we chose an RCC frame with a filler slab as our primary structure. This decision significantly reduced material usage of up to 30% less concrete and 20% reduction in steel reinforcement, which helps reduce the dead load. For the envelope design, we've used agrocrete blocks for walls, an innovative material that makes use of agricultural waste, which is 25% lighter than conventional masonry and reduces structural load, leading to further savings in materials. For HVAC, for HVAC, we adopted a multi-split HVAC system limited to specific lab spaces. On the east and the west wings, these zones are used only during operational hours, keeping energy usage minimal while ensuring comfort whenever necessary.
For waste management, based on projected daily waste generation of approximately 1200 kg, our strategy includes on-site composting of biodegradable waste to be used in landscaping and segregation and collection of recyclable, hazardous, and general waste for processing by municipal or partner facilities.
So for innovation, we proposed a partnership with the farmers and outside professional to help in the urban farming and the facade systems. In urban farming concept, we have a farm to table concept where food waste coming from the dining area is being composed in the terrace compost pit, and it further has been used in planter boxes and terrace farming. Planter boxes, south facade of a building experience. So what was the problem? The south facade of the building experienced a high solar exposure, and it increased the indoor temperature, raising cooling loads and energy consumption. Solution, we proposed a manually operated green facade integrated with the planter boxes. Adjustable panel enable real-time control over sunlight penetration and reducing the heat gain. Optimizing daylight, prevent glare with maintaining natural light intake and reducing artificial lighting needs. Trellises. So in trellises, we have proposed applied it on the east and west facade where there's a maximum radiation. Use of bamboo rather than using steel, so it was most cost efficient, carbon efficient, and locally available since Madhya Pradesh is the highest production of the bamboo. Trellises. So so we have divided into four of the plants in the trellises where they give thick leaves thermal insulation, thick leaves absorption heat, and filters pollutant in all the zoning areas of the east and west facade.
Coming to health and well-being, particularly thermal comfort, our first step was thermal zoning. We placed washrooms and staircases along the east and west facade to act as thermal buffers for the main learning spaces. The east and south facades feature modular planter walls functioning as double skin facades that reduce heat gain and support evapotranspiration. Filler slabs with embedded terracotta pots were used to increase thermal mass and slow heat ingress. Our agrotreat walls further enhance thermal comfort by being breathable and insulating. We leverage the stack effect through vertical voids and courtyards, encouraging natural ventilation and passive cooling across corridors and classrooms. To tackle heat, we used evaporative cooling through water bodies and vegetation. Each facade is designed as per their orientation. So the east and the west have low window to wall ratio of about 20%. The south, sorry. The south has moderate wall to window ratio of about 30 to 40%, and the north has high wall to window to wall ratio of 40 to 50% for soft diffuse daylight. We did a thermal comfort analysis based on solar insolation between 8 a.m. to 4 p.m. on summer and winter solstices. In summer, low insolation zones are created, keeping these areas cool and comfortable. In winter, south-facing courtyards having insulation zones make them warm and usable even in cooler months. These seasonal shifts in heat gain allow the adaptive comfort of open spaces, reducing dependency on active mechanical systems.
Moving on to energy. So this graph actually shows you the different types of appliances that a schooling industry has, and the total that we have comes up to approximately 1525 kilowatt hour for one day. And then moving on, we have the entire radiation analysis for our structure, which has all the passive design strategies. So for the roofing, if you see, it has the highest amount of radiation compared to all the other facades, and which also tells us it has higher potential for solar energy as well. So we have solar panels planted all across the roof, and to reduce the radiation even to reduce the radiation even less, we have green roofs as well. On rest of the facades, to reduce radiation by other elevation facades, we have green facades as well. We have trellises and other renovation techniques that we discussed earlier. And then we move on to the thermal simulation that we did. So this actually explains the thermal comfort based on solar solar insolation. All of these shows low insolation zones except for the zones near the peripheries which have direct sunlight. Hmm. And then moving on to daylight analysis. So we performed a daylight analysis on a typical flow plan. So the classrooms basically are within the range of orange to chrome to orange, which shows they have a minimum lux of 300, minimum lux of 300, which is the basic requirement for learning and writing spaces. We also did a SDS solar spatial daylight autonomy and in different orientations of our classes as well with their specific window wall ratio, and the minimum of 50% of the class is within the reach of 300 lux as well. So from this we can actually we have one more simulation which tells us the solar radiation for every flow for a typical flow plan, and the conclusion from is that the radiation is not entering the classes and it's only on the facades. And then the conclusion from all of these simulations can be that the students will be, since it's within the range of comfortable thermal capacity and lesser radiation, students will be using lesser cooling appliances. And moving on to generating solar energy. So we are using 60% of our terrace floor, which is 2,300 square meters for solar panels. We are planting 645 solar panels and we are generating uh, electricity up to 4.7 lakhs kilowatt hour, and and our energy consumption is actually way less than that, and the 20% of it can actually be given back to the grid. And this is the entire an annual energy consumption chart, which tells you the proposed cases, the operational cases, and the energy consumption. That helps us to make the comparison and how are we making our entire building net zero. So this is a basic graph that helps you deduce that how we are making the structure net zero. And then moving on to EPIs. So the first base case was 77, which was done from Yugantar Public School, which is again in Raipur, and it has a similar program. It has a similar built-up area. The target EPI proposed by SDI and ECBC was 34. The EPI that we achieved was, that our structure achieved, that the proposed appliances achieved was 19.2, and after using lesser appliances, we have 17.4. It's not working.
Okay, we had a slight technical glitch. We will be adding 2 minutes into the Teams timer, and we'll continue the presentation. So Teams, you can start now.
Moving on to water performance. So mainly there are two types of water, domestic and water, which goes into the domestic and flushing, which goes into the fixtures. So mainly we've tried to reduce 28 28% of LPCD by using low flow fixtures, sensory fixtures, and aerators. After that, the water goes into specific rooms like toilet, kitchen, showers, and other labs as well, and then further distributed into grey water and black water. The grey water goes into the municipal sewer line. The black water is going to the STP, which is being recycled for cleaning purposes, landscape, and then flushing. So from this table, we can draw the conclusion that we are using, like we have a rainwater harvesting system as well on our site. And using STP, we'll be recycling 100% of flushing water, 100% of landscape water, and the excessive water can be again used for cleaning purposes. Overall, there's a reduction of 20.5% in water consumption. This is the entire table that shows the proper water process of how we are how we are reducing the water consumption. And this is the landscape requirement. We have tried to reduce the water consumption by landscape by 66.4% by planting local trees. The STP we use here was small scale bioreactor membrane, which is economic, and it also compact, uses less space on site.
Embodied carbon. Our aim is to minimize this. Our aim is to minimize the carbon footprint building by reducing greenhouse gas emission throughout the entire building process. But after studying, the 60% of the carbon is being produced by manufacturing the materials. So my main focus was from the A1 to A5 journey, where how I am getting the materials from the nearby site, and I was aiming to get it from the 60-kilometer radius itself, where only one of the material, which is tipwood, was getting from the Nasik, which is from 400 kilometer away. And okay. So walls reduction, we have come down to 94.38%, where we are making the bricks on site because of the nearby farms. We are using the straw bales and the straws from the crop from wheat, soybean, and corn, and building a process with the company, and also the life cycle of the aggregate, which can be recycled again and again afterwards. The filler slab construction, which we have aimed to about 68.3% reduction, where we have compared, the table shows that the comparison between the normal RCC slab with the vitrified tiles and the filler slab with the terrazzo tiles, where it is about 30 to 40% lower in the embodied carbon. The green roof, we are aiming for 74.49%, where the reduction of the embodied carbon is around 20 to 40% compared to the normal concrete and metal roofing. The facade we have used 3 different materials. One is tipwood, one is terracotta, and the other is bamboo. So currently we were in increase of 37.5 because the transportation was from very far from the site, which is 400 kilometer. So we kind of covered it in the bamboo because bamboo is the locally available material. So this was the overall baseline of the from the Uganda school we referred to, where after comparing both the baseline and after proposing the materials we used, we came down to about 84.93% in reduction of the embodied carbon.
Moving on to resilience. So the main key problems on site are basically the wind speed, which is at maximum up to 9 meters per second, the dust storms because of the dry weather and the agricultural fields around, and the heat waves due, and the maximum temperature can rise up to 45 degrees Celsius as well in Indore. The solutions that we used to tackle these were vegetative barriers, green facades. We also have a backup energy. We have a generator on site which can store up to 1532 kilowatt hour of energy, of electricity as well, backup water supply, and then we all heat waves have been tackled by passive design strategies.
And then community resilience, we have a huge expansive dining area which can be used for use as a hospitality center as well in the future. And then fire resilience. So in terms of fire, we have actually abided by all the rules provided by necessary fire laws.
So to conclude, the intent behind our design was to make students empathize with nature and immerse them in various forms of learning, active, passive, indoor, outdoor, as well, like by incorporating programs such as urban farming and composting, taking responsibility of planter facades. So the idea was that they not only learn about sustainability but actually live it. So, thank you.
Thank you, team. Round of applause for them, please. Okay, so let's hear from the jury. I'll go with Sakit first.
So thank you. I really like the way you approached the spatial planning in terms of placing your blocks, the courtyards, the service spaces. So that I think that you started on a very strong note there, and then integrating the landscape and trees on roof and your planter walls are all very commendable. My question is, one is about lighting and one is about energy consumption. Okay. So did you try to get like 100% daylit classroom? Because your maximum energy load is coming from lighting, right? And north light is good for classroom, and you had the opportunity to get light from north in all the classrooms, right? But you are shading some of the classrooms on the north side by corridor. So I was not sure on the reason behind that, right? Follow-up question is also about the orientation of your sports block. So the other two blocks are oriented as per climate, sun path, but what is the reason of the orientation of, right? Okay, I'll stop here.
The main reason for using the direct north light was firstly that we have very strong cold winds coming in. So for primary kids, it would become really cold during winters. And the reason for the sports facade was that like if you see the plan, we have the swimming pool closer to the south courtyard. So it was like it was a strategy also of evaporative cooling during summers, because we have a jali facade near the pool. So again, the pool would act as a water body and cause evaporative cooling for that.
Okay, thank you.
Yeah, Elise.
Thank you for your work. I also really appreciate the architectural design. I think also you compared to the report where I was sometimes not understanding some points here, it was super clear, and I really appreciate like what you've done with also like the sensibility with the person and the design. So it was a really great point that you did. I have a question regarding actually the facade. So you have it placed on the south facade, like the plan facade, and so you aim at making it rotating.
So during winters, you actually rotate it, so you can make
So
it
perpendicular like that,
yeah,
or how do you?
perpendicular to the corridors, so that you let heat and light inside the classrooms as
Mhm.
well. And then during summers, it's parallel to the corridors, so that you're blocking or reducing the heat actually.
Okay, so the idea is not from like during the day not to move them, but then seasonally to actually
Yeah.
move them.
Yeah, and then the planter boxes actually, they can be like they can slide, so it's easy for the students to use. And they also have a drain tray because we couldn't provide pipes to go through and through the facade, so the excess water collects in the tray and then it's
So actually no automation, it's just the
manual, yeah.
manual, which is actually fine if you have like children also being aware of they need to do that to improve their comfort. I think it's a good idea to make it manually. Okay. I leave it to you. I have my next question for after.
Yeah, okay, yeah, second.
Okay, all right.
Yeah,
I know I really enjoyed the fact that at different stages in your presentation, you're focused on user experience, and that's something which, we tend to forget. In the end, it's about the students, the kids, and the people who are going to occupy it. In different places, you've spoken about the experience, and I'm really happy to see that. We tend to get lost and carried away with just the architecture, but in the end, it's for people. So that's really nice, and of course, I missed engineering throughout your presentation. I was looking for it. I think this comment has been up, but just one clarification you can help me with. At some place you spoke about the use of green roofs and how that helped you reduce the embodied carbon. I'm not sure of how that was done. If you could sort of elaborate on that. Sequestration, acha.
Okay, so if you see the section of the so the layers which I have proposed, the material to cast, it's like in normal cases we cast a full slab of 150. Here we don't have to. So I was thinking that maybe reducing the slab depth and then increasing it by more layers, so it can reduce in the cost. So you can it is not a very drastic change overall, but inside if you see the classrooms dynamics has been changed because of the roof is being green roof. That's why.
Yeah, but from an embodied carbon perspective, so what you're saying is that you reduce the thickness of the slab,
Yes.
but you have heavier, components on top of it now. You would actually have to enhance the thickness to even support a green roof. I mean, that's what would normally happen. But the other point, probably, I think what Saket is saying is something which you might think about. That sequestration, I didn't think about it myself. Maybe that's another way of putting this across,
Okay.
But I think, again, it's good to have this idea, test it through. Some of them are actually really common sense, but you'll have to really take it through to a little more detail, get into it, because in the end, whatever you're doing here in this contest is also something which you want to practice. Your clients are going to ask these questions, and you will not be able to pull this off unless you have the data to back it up, right? So it's some, a little bit of effort there. I mean, while a form is good, all your clients want to have a functional building as well, right? So an emphasis on that will be really appreciated. Thank you so much for your effort.
Thank you, sir.
I had just a small representation comment, I think on slide 31, and on the way you communicated the information. So here, exactly, you do radiation, and then you say it's good for your PV panels. You have them on the roof, but then you do the irradiation on the roof and not on the panels, I think it would like strengthen the way you communicate it, saying, okay, actually I have my PV there and then I have that much irradiation and it's good, because here you have the PV and you don't know if like they'll get good irradiation, it's you've done it on the roof. So maybe for convincing your client, think about that, what you want to show. Also no legend, but I guess red is good irradiation, right?
Yeah, thank you, jury members. Thank you, team. Round of applause for Team Solar. Let's take 5 minutes and get the components in and out. Our fourth presentation is from Team Diflow Spark. Their project is based in Tarapur, Boisar, Maharashtra. The team proposes terracool coolants, terracotta jalis to bring about their passive survivability of their building. Teams, you will have 20 minutes to present your work to the jury. At 15-minute marks, you'll hear this bell. And at 20 minutes, I'll ask you to stop your presentation. After that, you'll have a 10-minute Q&A session. Please keep your answers direct and to the point. The stage is yours.
Hello. Building the future, the climate smart city in Tarapur. Good afternoon, everyone. Myself, Disha Ganesh More, with my fellow teammates Yaunik Mistry, Soham More, and Prathamesh Parab. Together, we represent our team, Diflow Spark, from Viva School of Architecture. Our project partners, Craft Spaces, and our industry partners, Green Jams and Nitin Naik Associates, developed for Tarapur Vidya Mandir School. The project is situated in a Tarapur Boisar district of Maharashtra and industrial town in a Palghar district. The total site area is 16,219 square meter, which includes an existing school building.
Team, please speak on the mic.
The proposed development focuses on a specific site area of 5,766 meter square. The site is flanked by industrial zones on both the north and the south side. Conceptual massing. The initial massing is conceptualized as a simple rectangular box organized through a grid
Team,
framework.
is the mic on? Can you check? Okay, please keep it close to your mouth. Yeah.
The initial massing is conceptualized as a simple rectangular box organized through a grid framework to establish a clear design. We subtract the central portion of the mass to create a central courtyard, creating a communal core within the structure. To maximize natural light and cross ventilation, windows and open passages, balconies are integrated around the central courtyard and on the exterior facade. The final form achieves a balanced composition of solid and void spaces. A key feature is the open to sky amphitheater that connects with a staircase, encourage interaction and movement. From this, the thermal analysis was done. So, the south-facing facade optimized for the shading during summer to reduce heat gain. In winter, south glazing allows passive solar heating for energy efficiency. Shadow analysis ensures maximum natural light penetrations into the indoor space. On zoning, the central courtyard as the focal space, staircase course on two sides for easy circulation, classrooms, staff rooms, libraries, and computer labs placed on the north and south sides for optimal light and ventilation.
This is the site plan of our proposed building. The site plan is demonstrated in the integration of new sustainable school block with the existing campus. The proposed structure is placed on the eastern edge, respecting side-backs and ensuring optimal solar orientation with existing building which retreat to preserve continuity and functionality. Main entrance of the site is from the northwest side, which is clearly defined vehicular and pedestrian circulation. The layout is courtyard centric, promoting natural ventilations and daylighting. The building orientation and landscaping grading also supports passive cooling and efficient rainwater harvesting, making the site both climate responsive and contextual sensitive. Ground floor plan. The ground floor plan is centered around an open courtyard with sunken amphitheater at minus 0.5 meters, and the plinth is raised up to plus 0.6 meters to prevent flood in case. There are three access points for the main structure: from north as a main entrance, west which is from existing campus, and southern entrance. Service zone includes the septic tank and underground water tank. Detailed ground floor layout. The detailed ground floor layout strengthens fluidity and interaction. Classroom, staff spaces, and support functions are arranged along a continuous shaded corridors. The integration of green edge and parking of 22 bays to northern maintain a clean buffer and initiative navigation. First floor and third floor plan. Each floor is planned around the courtyard, reinforcing natural light and airflow. First floor is at a 4.2 meters. House classrooms, staff rooms, and gender restrooms, all placed for functional proximity and surveillance. Second floor is at 8.4 meters, including additional classrooms and combined library, computer lab, and zone to encourage collaborative learning. The third floor is at 12.6 meters, hosting a large seminar room, doubling as multipurpose spaces for students, leading activity and community engagement. Building sections. These 4 sections clearly express the vertical organization of passive strategies embedded in our design. The central courtyard is partially climatic core, enabling natural cross ventilations and daylighting across all the floors. Section A and D illustrate how the amphitheater at the base interacts with academy. Section B highlights the depth of classroom base, funneled by terracotta jalis facade that act as breathing skins, reducing heat while allowing diffuse light sections. Section C reveals vertical circulation with open staircase and landing that remain shaded and ventilated during whole day. Elevations. These 4 elevations reflect a careful balance between modern utility and vernacular expressions. On the solar exposed north and south facade, we used a mix of terracotta jali, vertical shades, and deep set windows, helping mitigated solar gains while maintaining visual connectivity. East and west elevations are opaque and more grounded, offering insulations from the rising and setting suns. Techniques. Construction techniques. On the top left side, we can see a diagram that details the integrated water dripping system for evaporative cooling water tank looping, which is eventually distributed across the terracotta jali via pipes, concealed with MS frames. This enables passive cooling while eliminating excessive energy use. On to the middle diagram, that explains the drainage strategies. Water run flow from the wet jalis is channeled through concealed slopes frames to avoid stagnation and seepage, enhancing both thermal comfort and facade durability. On the below left side, the column beam slab joinery is reinforced by 12 mm dia stirrup at 180 mm center with bent up bar to ensure reimbursed load transfer between horizontal and vertical element. The right hand side below, the base isolated raft is introduced as a mitigated seismic risk at the site is located in earthquake seismic zone 3. The structure incorporates lead plug isolated stainless steel plates with flexible materials at column footing junctions. The components absorb lateral vibration and allow safe dispersions of seismic energy. Fixtures, waste management, and the fixtures have been selected for high efficiency and durability. These includes LED tube lights, fans, exhaust fans, spotlights, all consuming minimal power while enhancing interior comfort. A solar panel array is installed on the flat roof. It orients and title maximum solar gain through the year. The anthropometry section illustrates the vertical sagging of classroom spaces, terracotta cladding, and shading fins. Internal layouts reflect ergonomic features, design, and optimized daylight penetration. Waste management is streamlined through a 3-tier segregation systems. 60% organic waste, mostly from garden, is composted and reused as mulch on-site. 35 inorganic waste is sorted and sent to authorized recycle agencies. 5% is securely stored and sent to certified recyclers. This measures promote circulation, resolutions, environment, and clean campus operations.
Collaborative innovations. Our collaborative innovations is a TerraCool coolant in which there are 4 components. Wet terracotta jali, Warm air passes through the wet jelly, causing evaporation. The cools the air. Air outlet. Hot air rises and exits from the upper vent, enabling passive airflow. Water dripping system. Pipes evenly distributed water over the jelly to keep it wet without waterlogging. Water gutters. They collect used water and they redirect it for reuse, creating a closed loop of system. Now we will see a working demo of our innovation. Passive strategies for sustainable cooling. Evaporative cooling wall lowers temperature using water on terracotta. Cross ventilation enhances airflow through opening and lowers. Stack ventilation removes warm air via vents. Vertical fields reduce heat and glare while letting in natural light. Blue arrow indicates cool air entering through the wet terracotta jelly panels. Red arrow shows warm air rising and exiting through higher vents using natural convection. This airflow pattern ensure consistent ventilation and indoor cooling without mechanical system. The temperature resilience of terracotta up to 800 degrees Celsius helps to saving 30 to 70% energy by reducing the need of artificial cooling. Aggregate Aggregate blocks are made and used in building construction. These blocks are created by using leftover crop material like rice straw from farms. The material is mixed with the natural lime binder shape into the blocks and then dried. Aggregate blocks are cheaper and better at keeping building cool compared to regular clay bricks. They are also more environmentally friendly. The walls assembly includes precast aggregate blocks joined with the lime mortar and finished with the lime plaster layer, making it a sustainable and energy efficient construction method. The thermal map shows temperature distribution on each floor, highlighting warm and cool areas where the design improvement like shading or ventilation might be needed. Wind diagrams illustrate airflow and pressure patterns around the building, guiding natural ventilation strategies to the improve cooling and air quality. Air purifying plants are Erica palm and aloe vera improve the indoor air quality by removing harmful chemicals like formaldehyde, xylene, and benzene, and the adding moisture. Aloe vera also release oxygen at night, making it a deal for calm space like libraries and lounges. Mental well-being is supported by the fixtures like a green courtyard, open air, classroom, and amphitheater, which encourage interaction with the nature and enhance the learning experience.
The energy consumed by the building is 91,513.74 kilowatts, and the energy generated by the building is 1,26,000 plus 26.75 kilowatts. So the EPI, which was 100.79, is came down to 28.58 kilowatts per meter. So we have reduced the EPI by 72, which also calculated when the maximum amount of fixtures is consumed. So when the energy is not at its peak, the EPI will be reduced by 30 to 40%. For 1,000 to 20, for 1,26,000 26.75 kilowatts of energy generation, we have provided solar panels which are of 1.7 square meters, which provides the output of 320 watts. The generation of the energy peaks in the month of the March and April. The envelope of the building includes two types of assemblies. The first is for the wall window, and the second is for the terracotta. So we have used the walls which are like for the 12 internal line plaster, and the wool insulation, which also helps like for cooling, and the waste like the 50 insulation layers helps for the walls to cool from the heat which comes. The slab is made up of green cement and steel reinforcement. The water consumption is for the 939 students initially required for 45 liters per day, which resulted in a total consumption of 42,255 liters of water. By implementing the water saving strategies, the per student requirement was reduced to 16.6 liters per day. This led to the new total water consumption of 15,587.4 liters, which helped us in saving 26,667.6 liters of water. Rainwater harvesting yields 1 lakh liter annually with peak collection in July and June. This is the monthly breakdown of the water generation treatment usage based on the occupancy and seasonal irrigation demand. These are the water saving technologies like dual flush toilets, dry urinals, and flow regulators for efficient usage. It also helps explains how wastewater is treated through primary and secondary processes for reuse. A range of sustainable materials such as aggregate blocks, terracotta jali, cork tiles, and green cement are utilized to minimize embodied carbon while moving thermal and acoustic comfort. These choices promote environmental responsible and durable construction practices. The proposed building system achieves 47% of reduction in embodied carbon emissions through the strategic use of low-impact materials. Significant improvements are seen in the wall, roof, and fenestrations of the component. To achieve the annual generation of 1,26,000, we have employed monocrystalline solar panels, which helps us in also reducing the carbon emission. The resilience, which were like for the rising temperatures, the Boisar has a tropical climate along with the industries and the urbanization. It intensifies the urban heat island. So we have used the passive cooling techniques like shaded courtyards, ventilated classrooms using we have coolant techniques to keep the classrooms cool. And for the stormwater management, we have provided rainwater storage tanks and which are permissible to the landscape. And as we have the ground floor which is empty for the water logging, it will also help for the people to accommodate when there is a situation like this. And for the earthquake vulnerability, we have provided seismic resistant design and emergency preparedness measures. So as the site is located from the industries, it has a noise from the industries and also some fire and industrial hazards. So we have taken measures for the evacuation plans and also providing soundproofing materials like wool and designing the classrooms with the central courtyard, which will lessen the noise and it will act as a buffer. So these are the evacuation plans which we have planned. Financially, the construction cost is estimated to 71.5 million with a potential bank loan covering 60% of this amount at 10% interest rate. The daily cost per occupant is set at 13.3, making it affordable for construction workers. The project aims to recreate a sustainable learning environment that benefits students, teachers, and community by integrating energy efficient strategies and renewable solutions. So this is the flow of the loan and the tenure which we have provided for the costing, and through this we have a total interest of 1 lakh for 9764. It will achieve the net zero status through solar panels, water efficient fixtures, and while using the aggregate bricks for carbon negative designs. The interior will feature eco-friendly furnishing made from recycled plastic, and rainwater harvesting will support sustainable water management. Overall, the building will have total area of 92,989.42 square feet with the daily water consumption of 42,225 liters and electric production of 276 kilowatt hour per day, ensuring structural integrity and safety. Yeah, that's it.
Elise, I'll start with you. Yeah.
Thank you for your presentation. I thought it was really clear. I also understood well your report, so thank you for that, for highlighting everything. today. I have a question regarding your Tiflos Park. Terra Kulkulen, sorry. So you say the idea is to have the evaporative cooling, so you have half of your facade which is glazing, nothing, and then the other half which is like they use the terracool as a jelly and then making the the air fresher into your building. The question is, like, how do you operate it? Do you have precise time? Like, is it always in operation? Do you use it? Do you put the water also in the winter, in the summer? How do you regulate that?
So it will have an humidity sensor for each month. Like we have different types of with different levels of humidity. As the site is located in Palghar, it is hot and humid. In the month of May, June, the temperature rises. So due to which the water will only function like it will detect the humidity level due to the temperature and the level in the indoor and outdoor spaces of the and according to it the water will flow.
Okay, so it means you would have a sensor for every classroom, and then for every classroom it will be put into operation or not. It's what?
Yes.
Okay. And I also have a question like same system, but regarding the water need. So how is it working? You have a loop, and then some of the like it will be evaporated. So how do you deal with the water topic?
So we have an SBI irrigation system, and also we have a rainwater harvesting, which will be used throughout the year, and the water will be taken from the recharge wells, which will directly go to the OHT, and then from that through the ducts it will be provided to all the different parts of this terra coolant.
So it will be all harvested water. Actually, what you use for the system, it's not water from the tap or from somewhere else. It's just what you harvest at the end.
Ma'am, I didn't get the.
No, I was just rephrasing if I got it correctly, but I think I got it correctly. Yes. Okay. Thank you.
Yeah, Sumit. Yeah. Thank you. What's behind the name, team name, Diplo Spark?
It's from the letters of 15 members of our, so the Diplo Spark means everyone has their first initial, and from that we have created the name.
It must have taken some effort, I can say, to make sense of that. Or you've chosen team members to make that work. But anyway, good. And just one sort of observation on the embodied carbon side. So you said that the roof and floor embodied carbon reduced in the proposed case compared to the base case, but I could not figure out anywhere in the narrative how that happened and what did you do differently on the roof or the floor to make it less.
So for the floors we have used green cement, which will reduce the carbon rather than using the normal cement, and using green cement it will reduce the carbon emission accordingly. Like also for the roof also we have added that only with the steel reinforcement. It will also have an coating which will help in reducing the carbon emission.
Is that was it there? Was it part of the presentation?
Yeah.
It was. Did I miss it?
So for the embodied carbon, we have added the green cement for slabs.
All right. Just one other comment on this. Very interesting. When you've done your daylight analysis, did you factor for this facade, or is that analysis without it? Because I can't see these two things working together. So, if you could pull up one of the simulations, whatever.
We have an window over there, which is just besides the. So one classroom will have an wall of terra coolant and also a window.
All right.
And the window will have the fins, which will stop the harsh light, which will enter into the classroom.
Which way?
And also for the daylight, we also have an option to for this terra coolant will block the full light, so we can add light sleeves at the top of the wall, so that will also increase the indoor light, and the also it will give sunlight exposure more.
Well, so Which way is the board, the in the classroom? Do you have an interior plan somewhere, or maybe in this? The facade is on the south side, isn't it? Yeah, and see, yeah. So you have the facade on the south side, partly the jali and whatever the terra coolant thing, and partly a normal window. All right. Okay. Yeah.
So a lot is happening, right? But for me to make sense of it, I am really confused about where the north is. Okay, so can you open the site plan and show me the north in the site plan first? Okay, hold on. Yeah, okay. See, go to the next slide. Yeah, so now the courtyard has changed. Yeah. Go back one slide. Yeah, it's in this direction, and now go to the next slide. So which is your right orientation of the
Sir,
court?
actually we found this mistake and we tried to rectify, but the north is actually in this direction.
So this is the correct. This is the correct drawing.
It is flipped by mistake.
Okay, this is the correct.
This is flipped horizontally.
This is wrong then.
It is placed wrong.
No, so show me the correct
It
orientation.
is like from this direction. It is like mirrored. So by mistakenly we placed the north in all the plans in the flip direction.
Is the arrow wrong or is the plan?
The arrow is wrong. The plan is correct.
Okay, so go back
like
one
while
slide.
placing the arrow,
So now the courtyard is in this direction.
the courtyard will be like in the vertical direction. Means in the south is at the bottom left of this, and the north is at the top right.
Okay.
So it is tilted at the 29 degrees or the right side of the top.
So forget the north direction. Tell me which is the orientation, which is the correct orientation for the courtyard. Is it long in this direction?
Vertically.
Okay. So this drawing is also.
The drawings are correct. The north is like placed mirrored. The symbol of the north.
Which
Yeah,
plan is
The courtyard
correct?
is opposite to the direction of the buildings. It is not parallel to it.
Can you tell me where the classrooms are there in this plan? This plan is correct, right?
The classrooms are just below the solar panels.
Okay. But यहाँ पे तो है ही नहीं.
Next.
This is ground floor.
Sir, on the ground floor there are no rooms or something.
Okay.
It is cantilevered till the first floor.
So
The
show me a
classrooms will
first floor.
start
Show
from
me
the
the
first
first floor.
floor. So the courtyard is located over here at the center, and the classrooms are placed on both the horizontal sides.
Okay. All right. So thank you for that clarification. I'm still having some confusion, but okay. So my comment is one about the daylight, that this is very good, but I'm not sure if this really hinders in daylight penetration, right? Second comment is, if you have this, right, the functionality of this totally depends on air flowing the way you are drawing the arrows, right? So what ensures that air would come through this into your classroom and then go out? How do you create that buoyancy difference?
So we have an courtyard at the center, which will like help us in the movement of air.
Have you done some simulation to see if it actually works like that, or you think it will work like that?
We have referred case studies for this, like which have a central courtyard. So referring that, we have planned this.
All right. Thank you.
Yeah, Alice, you want to add anything or? Yeah. Okay. Thank you, team. Thank you for the presentation. Give a round of applause for the team. So we will be having a long break since this is the 4th team, and we'll be back here by 2:30. So folks online, stay tuned and cheer for your upcoming teams. We'll break for lunch, and to all the teams, keep your component models outside in the table so that jury members can have a look in their free time, and put it under your banner, respective designated banner spots. Okay, yeah, we can move on.
Solar Decathlon India, what's it all about? Net zero building, what's that all about? Solar Decathlon India, what's it all about? Net zero building, what's that all about? Is it cool? Is it hot? Is it drool? Is it fat? What's that all about? Real world problems need innovative solutions. If you don't act now, there will be implications. Is it hot? Is it cool? Global warming will be cruel. You will form a team with the same desire, going for the moon, shot forged by fire. We use technologies and crazy simulations. We learn to design with new innovations. So what you waiting for? No procrastination. Get off your butt, come join our workstation. Solar Decathlon India, what's it all about? Net zero building, what's that all about? These problems are tough and complex too. Your partners are there to help you get through. This challenge is exhausting, intense, it's a drill. These 10 mad contests will sharpen your skills. Net zero energy, water and stuff. And affordable too, that's crazy enough. Solar Decathlon India, heck it's really tough. But your attitude and grit is more than enough. Get your hands dirty on real world projects. You're gonna learn more than your specialized subjects. Solar Decathlon India, what's it all about? Net zero building, what's that all about? Cutting edge, butting edge, climate wedge, make a pledge. Do it all, save it for a lonely planet after all. Understand, climate friend, take a stand, make a trend. In the end, recommend your ideas will have defend. Are you hot? Are you cool? Are you gonna be a fool? Zero heroes are here to stay. So what you waiting for? Come join this play. Net zero building, that's what it's about. Solar Decathlon India, that's what it's about. SDI.
Pick a site on a railway track. Put your building on an earthquake crack. Cutting million trees and planting roads and houses with their electrical loads. Dumb ways to build, so many dumb ways to build. Dumb ways to build, so many dumb ways to build. Put your building facing west. Make a toast of every guest. Concrete, steel, here and there. Carbon emissions to poison the air. Dumb ways to build, so many dumb ways to build. Dumb ways to build, so many dumb ways to build. Forget to put a bathroom drain. Add handrails that cause you pain. Elevator shafts that taper down. Bad staircase trip over your gown. Dumb ways to build, so many dumb ways to build. Dumb ways to build, so many dumb ways to build. Start building with no hard hat. Walk barefoot, toes go splat. No gloves on, no goggles too. I wonder what these wires do. Dumb ways to build, so many dumb ways to build. Dumb ways to build, so many dumb ways to build. Building on a melting glacier or a floodplain. Letting all your rainwater run down the drain. Heat the earth enough to fry
Build less, build smart. A message from Solar Decathlon India.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from S The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through.
Hello, everyone. Welcome back to the Educational Building Division. We will now continue with our presentations. For our fifth presentation is from Team Nayara. They have worked on project Pride World City School in Charoli, Pune. Teams, open up your presentation. You can hold it. Okay, team, you will have 20 minutes to present your work to the jury. At 15-minute mark, you will hear this bell. You won't have a 21st minute, which means at 20 minutes, I'll stop you and ask you to stop and end your presentation. After that, we will have 10 minutes of Q&A session. Please keep your answers direct and to the point. Okay, team, the stage is yours. All the best.
Good afternoon, everyone. We are Team Naira and we are honored to present our architectural design under the Educational Building Division. Our esteemed project partner is Abhikalpan Architects and industry partner Eco STP and Green Gems. Representing Vesqua, we have aimed to create a space that not only fulfills academic needs but also inspires learning, interaction, and innovation. Our team is led by Riddhi Bhantia, our leader, and following are the team members Tejas, Mir Murkar, Vedika Mokal, Haley Shah, Amisha, and Vinit Javle. This slide highlights the core sustainability-driven goals we have targeted throughout the design process of our educational building project. And energy performance, we have achieved a net zero building with an EPI target of 27 kilovolt per square meter per annum. Energy operation, we are able to reduce greenhouse gas emissions by 20%. Affordability, we have 20% reduction in capex and 15% in opex. Embodied carbon, we have reduced carbon emission by 62% throughout the design. For health and well-being, we ensure that occupants experience thermal comfort in the range of 21 to 25 degrees Celsius. On water performance, we have reduction in 64% of water. And as a part of a resilience strategy, disaster response phase capable of supporting 3,000 people for 5 days. The selected site is in Charoli, Pune, positioned at the elevation of 560 meters above sea level. It features a warm and humid climate, making it ideal for designing passive cooling strategies. The prevailing winds are from the west, and the secondary winds are from the east. Solar orientation favors passive daylighting on west and south facades. Our site is 160-meter long and 100-meter wide. Entry to the site is from the 18-meter wide road in the south, and adjacent to the site on the east is a proposed highway. It can accommodate 2,400 occupants and it is shallow and drainy. The site contour suggests natural rainwater runoff and depression areas which influence drainage planning. Our form is designed to create an engaging, comfortable, and climate responsive educational environment. The process began with orienting the building towards the north, enhancing the to maximize natural daylight. Then the blocks were then rearranged vertically to provide shaded structures and improve comfort. A curved shape form was developed to diffuse direct solar radiation, enhancing thermal performance. This form was flipped on the western facade to break continuous exposure to daylight, ensuring no single surface absorbs too much heat.
Let me ask you a question. What if your school day began not with a bell, but with birdsong, sunlight, and the scent of trees? So talking about the site level strategies, let's start with the depressions which were already on the site, which was used for water body to support evaporative cooling. The next is the cut fill plan, which we used the technique to minimize the earthwork disruption. Next is the China mosaic tiles, which was used on the rooftops to reduce the heat island effect. Next, talking about the amphitheater space, which was again used through the, which was again created using the contour lines, and a sandpit was created. There are open library spaces and reading space, which are created in the walls. Next, talking about the bus parking, which is created at the corner of the
Team,
site,
please have your mics up. Yeah.
which is situated at the corner of the site, which ensures reducing the carbon emissions in letting inside the site and the noise levels from outside the site. The mated landscapes ensures safety and sensory play. Cycling path inside the
Team, can you stand on the line or behind it? Yeah, thank you.
cycling path on the entire site ensures sustainable transport and movement throughout the site. The water body is placed in the windward direction to pre-cool the incoming winds. Talking about let me quickly walk you through the site planning. Site is divided into four clear paths, which is the carway, which leads you directly into the basement, the main pedestrian spine that merges from the entry, the zebra crossing, and the cycling zone. The bus route, which dips into the lower contours to keep the emissions away. The cycling path follows the slope, offering views and pond and structure. Now, talking about the building level strategies, there's a large amphitheater which overlooks the pond and gives a panoramic view of the structure, which is the iconic first impression of our site. The light wells have been used as pockets for stack ventilation and also to provide light for the under classrooms. The voids act as breakout spaces for kids to have playful time. There are multiple angle planes on the western facade to deflect the direct radiations of the sun. Evaporative cooling through the pond helps us create a microclimate under the structure, so that the winds coming from the southwest direction cools the interior. AI sensory fins are used on the eastern facade to get controlled daylight and minimize the direction. There are interactive classroom spaces inside. The southern facade has less usable rooms or corridors, so that is why we have used screening of rods over there. The circulation has been divided into a zigzag pattern, which breaks the monotony and helps to reduce congestion on one space. The building approach from here is seen. So the timetable here has guided our layout. So we have divided the timetable into zones of each timing and the space which we have provided. So the morning has been used as classrooms and corridors from where the students will pass. The midday has been broken down into breakout zones. The afternoon has been used as clubs and play areas. So spaces are zoned by time and age. Quiet zone are used for younger students and the active zones are used for older students. So talking about the sectional knowledge. So here we enter through a contour sensitive path, which has been greeted by an open air theater at the entrance, which also engages and is a social pause point. Walking past, there's a cool breeze which comes in from the water body present below and which pre-cools the wind and also creates a microclimate over there. There are stack ventilated voids which are present, the blue, yellow, the green and the red ones, which help for airflow of the wind in overall structure. As you move inside, the light filter from the skylight and light wells, guiding your path to the wide and ventilated corridors. Children play near a biophilic wide opening where the tree is present inside, engaging the outside with the inside. Voids frame views across the levels, creating visual connections between one student with the another.
Team, please have your mics up.
Sorry?
Mics closer to the mic.
There's a bridge, which is the main spine of our design that actually brings in the winds and cools the entire structure. Um, the Y columns in the structure helps you is actually maintaining the load of the entire cantilevered part. So this is the playground area where students play and enjoy their break times. So it's a contoured path. Moving on to another. So in this, the cycling path winds naturally, um, weaving through the contours, making the journey playful, and it gives a sight to the entire structure and the pond. Next. The system works by circulating chilled water through ceiling mounted beams. As warm air rises from the classroom, it comes in contact with the chilled beam, cools down, becomes denser, and sinks, creating natural convection without using fans. All these are integrated with the IoT technology. Building management system supports users, including student, faculty, admin, security, and maintenance staff. Key features include energy and water monitoring, HVAC and lighting control, attendance tracking, GPS burst tracking, access to educational content, and room availability check. For focusing on engineering part, uh, the building profile, which shows a curved layout supported by a coordinate grid of column and beams. This form responds to environmental and orientation and also structurally stable. We have detailed the rough foundation section, which ensures uniform load distribution across the built footprint, especially suitable for site soil condition. Uh, Next, there are fence details and beam-to-beam connection details. Next. This slide showcases the construction details, which includes facade details, column section, and pad fitting, which makes structure
Can you
more,
please have your mics close and mouth?
more
Yeah.
stable. Next. Visual comfort is ensured through light shelves and light wells, which brings natural daylight deeper into the building, reducing dependence on artificial daylight and enhance indoor air quality. This building also includes transition spaces at entrance to buffer the thermal shock. Mental well-being is prioritized by incorporating spaces like breakout zones, amphitheaters. We have also integrated double-eyed multiple spaces that adapt for sports, dinings, and breakout areas, promoting physical activities. For inclusivity, features like tactile floorings or audio in lifts, universal washrooms, and ramps access are given. We have used eco-friendly materials like Khadi Prakriti paints, which is non-toxic and VOC-free. So in this slide, comparison the base case and proposed case across the key, three key environmental parameters: radiation, wind flow, and daylight. In the base case, high solar heat gain on the east, west, and roof increase cooling load with wind stagnation limit ventilation, and poor daylight penetrates leads to high artificial lighting demand. In proposed case, we given design uses passive strategies like vertical shading, optimized openings, and high performance glazing. So this improves solar control, enables better natural ventilation, and enhanced daylight access, collectively improving energy efficiency and supporting a net positive energy goals.
Innovations. We have used modular furniture design for easy reconfiguration of classroom spaces. Lightweight uniforms, ideal for Pune's warm and humid climate, ensuring comfort in every climatic conditions. Water conservation initiatives, students pour leftover water into the pond at the end of the day, promoting zero waste water. Climate responsive food plans, sustainable waste management. Kitchen food waste is disposed into biogas digesters, generating gas for cooking and creating fertilizer from leftover waste. Utilization of voids and dead walls. Modular exhibition spaces, which are used by modular pavilions, arranged in flexible manner for exhibitions and promoting adaptable use of space. Remote control fence. Mechanized fence used for climate control and shading, responsive to user input for changing environmental conditions.
in this project, energy performance is optimized through the combination of passive design strategies and efficient fixtures. Uh, key passive features include the building orientations, natural ventilations, and envelope design. Significance to reduce the energy demand. Energy consumption dropped from the base case 108 kilowatt 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 hours per annual into 27, and then thanks to both design and technology improvements, notably there are no need of HVAC during the winters due to the passive cooling. The rooftop solar panels contribute 1.4 million kilowatt hour annually, making the building net positive in energy.
Can you please have your mics close to the mouth?
The material choice also plays a vital role. Improve the wall and roof insulations significantly lower the U value and enhancing the thermal comfort. In the proposed case, the water demand per person is significantly reduced from 45 liters per day to 17.6 liters per day, primarily by using efficient fixtures like waterless urinals and low flow facets and WCs. Despite demand of the borewell recharging in nearly matching the domestic consumption, 6,500 kiloliters, whereas a demand is 7,500 kiloliters, reducing the dependency on external sources. Our waste water treatment system eco STP process 100 kilowatts per day. Treated water is reused for a landscape irrigation and flushing and farming, forming a closed loop system that enhance the sustainability and conservation borewell resources.
Embodied carbon. Starting with the wall assembly, we have developed a multi-layer structure designed for both thermal performance and sustainability. From the interior outward, the wall begins with 12 mm gypsum plaster, followed by 100 mm layer of rice husk insulation, followed by 200 mm agrocrete block, and finally the wall is finished with a 25 mm clay plaster. Moving on to the agrocrete block, this is the key element in our wall system and is produced entirely from agriculture waste on site. Moving on to floor assembly, we have used traditional techniques for floor assembly. It integrates Metacotta tiles which are made on site by the following procedures.
This slide highlights the building resilience strategies in response to the Pune's climate risk, water scarcity, heat wave, and local water logging. To combat heat wave, passive design strategies like evaporative cooling and integrated to maintain indoor comfort. Water resilience is ensured by increasing the water tank size to support 3,000 people for 5 days during disasters. Pandemic resilience is ensured with flexible openable walls that allows spatial reconfiguration to maintain social distancing during pandemics. Food resilience uses biospheres to filter runoff and manage stormwater, minimizing flood risk efficiently.
In affordability, low maintenance, low materials reduce the 25%, energy performance reduce the affordability in 75%, and water performance reduce to 64%. Cooling system reduce 27%.
So we started with a question and now we end with one. When students grow beside trees, under skylights and above water, are we just building a school or shaping how they see the world forever? This school redefines education through sustainability, inclusivity and self-sufficiency. From net zero design and water efficiency to gender-neutral breathable uniforms, student-grown green zones and income-generating community spaces, Every element is crafted to empower students to not just academically, but socially, environmentally, and emotionally. Because this isn't just about classrooms or corridors, it's about energy they create, the food they grow, the spaces they feel free in. Now ask yourself, is this a school or is this the blueprint for what every learning space should become? Thank you.
Thank you, team. You're well on time. Now we'll take questions from the jury. Saket, I'll start with you.
Yeah, thank you. A good presentation, especially after lunchtime. So you kept us very occupied. So thank you. I really like the entire architectural narrative on how you started and the shape evolved and how sensitive you were in placing different functions in different parts and at the same time being aware of the daylight and the ventilation. I like the way you integrated the water body in the contours and then built over it and using that as a way to cool the air and then so I think very good intent, very very commendable, and then the sensitivity to your envelope fins are all great. My question is, I would have liked to know a little bit more on the simulation in terms of, did you do a thermal comfort simulation to figure out how comfortable students are?
We haven't done the thermal comfort, but we we tried occupying the temperatures which was outside and then the inside temperatures after using the exterior facade and everything.
So how did you calculate the interior temperature?
Sorry?
How did you calculate the interior temperature?
Through the simulation only, actually we have put that in the report. It
Okay.
hasn't come here.
Okay.
We achieved, like the outside temperature was around 35 to 40, and then after using the orientation and everything which we have incorporated in the structure, later on we found out that the inside temperature was coming around 23 to 25 degree, 28 degrees Celsius.
28. Okay. Fair. Thank you.
Thank you for your work. It was really interesting to see super sensible work also. I really like the climate, like your axonometries, they were really helpful and super well designed. I also like the sensible use of void, what you said, what you wanted to do with the void of the spaces to make the children play with it and have access to everyone. So I really like this design. So architecture, very fine. What I'm a bit lacking, maybe, and it will be my question, is like how is the space conditioned? Because you answered the question from Saket, so it will be 20 degrees on the building, but how do you manage to go to up to 20 degrees? Do you have any active system?
Yeah, we have active system. Actually, chill beam we have incorporated in our structure.
On all the spaces, so on all the classrooms, or?
Yes, all the classrooms is HVAC and the chill beam which is going on.
Okay, and it's operated, you know that. When will it be operated? How you want to regulate that? Do you have an idea?
Can you repeat the question?
Yeah, the question is, so you have this beam that you, like chill beam,
Yes.
and then when will you put them into operation? Do you have a trigger, an automation?
Okay.
Which temperature should it reach?
After 10 p.m. we'll put that into operation because the radiations are high at that time, which we want the temperatures inside to be cool at that after that point of time.
So during the night?
Sorry?
So during the night, you say 10 p.m.
No, morning after 10 a.m. So sorry, 10 a.m.
Then all good, makes sense. Thank you.
I have a few questions actually.
Yeah.
If you have the time.
Go ahead.
So you have a product which is lined up here, but I'm not seeing it anywhere in the narrative. What is what is the plan?
This is the innovation which we have tried.
Yeah.
We can show
No,
you.
but
Yeah.
But did I miss it anywhere in the narrative? Because I didn't see a direct correlation with this.
No, we had incorporated.
Can you show me where?
On that side, the remote control based fence.
Yeah, no, as a product, yes, but I'm
Yeah.
just trying to see where in the architecture this was
yeah, that-
integrated into the
Yes.
building.
In the structure. So,
Oh, so all of these fins are.
so yeah, this is the fin which is outside the classrooms. You can also.
So,
Yeah, we
so you have
yeah,
a
it's in-
window inside and then you have the fin outside, is it?
Yes.
It's not a, yeah. So this is for
So there's
shading.
no direct fin which is connecting.
So it's for shading.
Yeah.
And how do you control that?
So the this layer which you can see, that is the fin.
All right, and how do you control that?
Initially we had thought of AI sensory fins, but then since it's a curved structure, so if in one classroom there would be some deflection using because of the heat or which is coming in, but since curve, other might have smaller openings. So there the light might get a little bit less. So instead we thought of coming up to remote based. So how each classroom will have the control for their side of the fins, which they can use
Operate,
it however they want, control it on their own basis.
Each of them separately done, right?
Not each.
So a
but
group of
suppose-
them.
Yeah, one room.
A room. It's very challenging. I'm sure you can imagine that. You spoke about chill beam system. What are the components of the system? Because I'm not seeing any narrative anywhere about the components of the system. How do you pull that out? What kind of a system is going to give you chilled water there?
The chilled water pipes are running through the beam levels. And they contain chilled waters in it, and they
Yeah. So anyway, where are the chillers? I mean, have you sort of factored for the energy consumption from that? I don't see anywhere any talk about chillers. What kind of chillers have you used? What is the cooling load for this kind of a building? Do you have that information, or did you figure that out? You haven't done that. One last question, Manish. Do you have time?
Yeah, we have.
I'm just trying to understand how you arrived at the shape, actually. Because if I look at the wind analysis which you have done, to me it appears that on the other side of it is actually a dead space. It's actually blocking the wind more than enabling it. I mean, that's how it looks to me. If you could take me through how you developed this. And the other challenge I'm seeing is also because the facade is curved and it's also mostly west, I think. What is the risk of the radiation being reflected from one into the other side?
So for the so how it arrived was the form development which we saw. So initially we wanted something that is shading the other part. So first initially we wanted the north facing classrooms because we wanted a much daylight. But then we have rearranged the block on one top of the another. And reason having the curved western block is to deflect the radiation, because on a flat surface you will get more radiation, and when you have a curved surface, in the simulation we have like we did a experiment of both, and then we saw that how much radiations are getting lesser on which end. So and then even this was getting radiation, so we flipped it on the other side so that there's like a multiple angled plane on the western facade. So there won't be one surface which will be flattened. Every surface will have like some deflection or curvature sort of thing happening.
So I would have suggested confidently putting some of the effort. I'm sure you've done some work behind it. Yes. It's not evident in the presentations. If you could have put some of that, it'll really help. Then it will show that you've done that effort. Otherwise, commendable work. Thank you so much.
Thank you so much.
Thank you.
Yeah, at least you have to be very quick about
Yeah,
it.
I just have a super small comment. I just want to highlight that you're the only group being 7-person. So the other groups are mostly 14 or 15-person groups. So for a 7-person group, it's like a huge amount of work. So congratulations for that.
Thank you so much.
Thank you, team. Thank you for your presentation. Let's take 5 minutes to move the model out and our sixth and final presentation is from Team Vidik Shah. They have worked on Pride World City School in Charlie, Pune. Teams, I request you to open your presentation. Okay. Teams, you will have 20 minutes to present your work to the jury. At 15 minutes, I will ring this bell. You won't have a 21st minute. That means at 20-minute mark, I'll ask you to end your presentation. After that, you'll have a 10-minute Q&A session. So please keep your answers direct and to the point. Okay, team, the stage is yours. All the best.
Hello. Good afternoon, all. We are Team Ved Viksha from VS College of Architecture and Institute of Technology, Mumbai. Our name reflects our philosophy: Ved for ancient wisdom, V for scientific understanding, and Sha for contemporary learning. Combining architecture and engineering, we aim to design a school that's climate conscious, culturally rooted, and user focused. Guided by mentors, faculty, reviewers, and experts like Green Jams and EcoSTP. This school project in Charoli, Pune is designed for 2,400 students and integrates learning with nature and sustainability. Set on an 18,100 square meter contoured site that slopes inward and includes 3 meter deep natural depressions repurposed as ponds, it harnesses prevailing wind from the west and secondary winds from the east. Surrounded by the residential and institutional buildings, the site is bordered by an existing road to the south and a proposed road to the east, with a future G+28 residential tower planned nearby. Our school design is inspired by ancient Indian learning spaces like Gurukuls, merged with modern educational needs. The architecture responds to the site's natural contours and wind flow. We orientate the building to maximize windward, windward westward wind penetration for passive cooling, while aligning with the terrain to minimize earth cutting. This gave rise to terraced roofs now used as green spaces and activity zones. The landscape is deeply rooted to Indian cultures using native, belief-rich plants that form a self-sustaining ecosystem and reduce water use. The site's 2-3 meter depressions were transformed into ponds inspired by Sun Temple stepwells, surrounded by interactive setting and self-cleansing aquatic plants that maintain ecological balance. The school is divided into two wings, one for juniors, KG to 4th, and another for seniors, 5th to 12th, ensuring age-appropriate environments. Classrooms sized at 5.5 meter by 8 meter are designed for ample natural light. Alternating floor plates create natural voids between blocks, enhancing daylight and ventilation while reducing the need for artificial lighting and cooling. These voids house open learning spaces like libraries and open gurukuls. A central people tree symbolizing the heart of the structure serve as a shared assembly space, reflecting the Vedic traditions. The amphitheater acts as a common zone for all age groups, uh, wherein the facades feature vertical fence and planter beds that regulate heat and bring in diffused light, while perforated floor slabs over courtyards cast playful shaded patterns for children. Sustainability, sustainability systems are seamlessly integrated. The school is independent and using borewell water and treating black water for landscaping. Grey water is filtered and reused for flushing, whereas the service tanks are located along the proposed road for easy maintenance access. Energy needs are met and exceeded through rooftop solar panels, allowing the school to feed excess energy back into the grid and generate revenue. In essence, our school is a climate conscious, culturally grounded, and self sufficient campus that blends traditional wisdom with modern technology.
Our project integrates real, cost-effective innovations that enhance performance, affordability, and replicability. A key feature is our intelligent HVAC and lighting system, powered by Meta's YOLO V8 model and OpenWeather's API. Using two cameras to monitor the zones, the system detects occupancy in real time. If at least 3 people are present and the outdoor temperature exceeds 28 degrees Celsius, the HVAC turns on automatically. For lighting, the system activates when even one person is detected and includes a 5-minute delay to avoid frequent switching. Each IoT module costs just Rs 6,000 and is optimized for edge devices such as Raspberry Pi, making the full system implementation across the school at approximately Rs 5 lakhs. This system reduces electricity usage, lowers operational costs, and minimizes the EPI and carbon emissions, making the school both eco-friendly and smart. We've also collaborated with industry leaders to strengthen our sustainability efforts. Green Jams provided us with a low carbon material that helps reduce the embodied carbon footprint. EcoSTP's on-site sewage treatment allows us to treat black water and reuse it for landscaping, contributing to our water self-sufficiency. Together, these innovations and partnerships have shaped a school that not only performs sustainably, but also sets a replicable model for future educational infrastructure. To reduce energy consumption, our project incorporates a range of passive and active strategies like courtyards, optimized building orientation, shading devices, and night flushing to help minimize the heat gain. Internal heat was further reduced by optimizing the opaque envelope as per Super ECBC guidelines, enhanced with vertical fins and planter beds to improve thermal performance. Energy efficient appliances are also used throughout to lower equipment loads. For cooling, we implemented a radiant cooling system that circulates water through the surfaces, reducing reliance on traditional air-based systems. This, along with the natural ventilation during favorable months and the shutdown of HVAC system during summer holidays, significantly cuts energy use. As a result, the total energy demand was reduced from 6.05 lakh kilowatt hour to 3.82 lakh kilowatt hour annually, giving us an EPI of 28. This site receives ample solar radiation, about 4.69 kilowatt hour per meter square per day, making it ideal for solar energy. We installed 710 south and west facing photovoltaic panels on the roof, generating more electricity than the building consumes over the year. This allows the school to achieve net positive energy status, reinforcing a commitment to sustainability and energy independence.
With regards to water, our project has achieved a remarkable 57% reduction in water demand, bringing it down from 45 to just 19.1 liters per person per day. This was accomplished using low-flow fixtures. Grey water from sinks and showers is treated and reused for flushing, while black water is processed on-site through an eco-STP system and reused for landscape irrigation. Rainwater harvesting plays a vital role capturing runoff from rooftops and other catchment areas. With 803 mm of annual rainfall, rooftop rainwater supports domestic needs during monsoons, while excess is directed to on-site ponds or groundwater recharge systems. In non-monsoon months, a proposed borewell supplies potable water for drinking, cooking, and ablution, ensuring zero reliance on municipal sources throughout the year. The landscape design is water efficient, featuring native and drought-resistant plants, xeriscaping bioswales for groundwater recharge, the efficient irrigation systems. Together, these strategies allow the campus to generate 72,224 kiloliters of water annually, far exceeding the demand of 25,833 kiloliters per annum. This results in net positive water balance of 46,941 kiloliters per year, making the school completely self-sufficient and sustainable in its water use. For resilience, our school is designed with strong resilience measures for emergency situations like fire, earthquakes, and pandemics. Fire safety includes clear evacuation plans, dedicated assembly points, and fire-resistant materials. The building is located in seismic zone 3 and is constructed with earthquake-resistant reinforced concrete and steel, along with designated open space zones for quick evacuation. For water resilience, rainwater harvesting supports non-potable uses like toilet and landscape, while drought-resistant plants reduce the irrigation needs. In case of pandemics or natural disasters, the school can support its population for up to 72 hours with secure food and water storage, backed by a reliable inventory management that ensures timely replenishment. Together, these strategies make the school safe, adaptive, and prepared for multiple types of emergencies.
Our building operations are managed through an integrated building management system, IBMS, that combines IoT and cloud-based technologies. This centralized system oversees HVAC, safety, security, water, and energy management, ensuring seamless and efficient building performance. A solid waste management system is in place where organic waste generated on-site is converted into biogas, which is then used in the canteen for cooking, supporting a closed loop sustainable system. To reduce structural load and material usage, filler slabs are used in non air conditioned areas like corridors. For conditioned zones, we've implemented radiant cooling systems that activate an hour before occupancy and include night flushing from 10 p.m. to 12 a.m. for energy efficiency. The total HVAC capacity is 200 ton using a highly efficient chiller with a coefficient of performance COP of 9.04 and a system wattage of 6.56 lakh watts. Expansion joints have been incorporated to accommodate thermal movements, preventing structural cracks and enhancing long-term durability. Altogether, these systems ensure high performance sustainability and operational efficiency throughout the building. The design prioritizes health and well-being through multiple strategies. In classrooms, especially those on the southern side, operative temperatures consistently fall within the IMAC comfort range for mixed mode buildings. Dedicated outdoor air supply system regulate indoor humidity levels between 30 to 60% for additional comfort. Classrooms are color coded to foster a playful visually comfortable environment that supports learning. The room dimensions 5.5 meter by 8 meter with a 1:1.5 ratio allow flexible layouts and ensure the teacher's voice is clearly heard throughout without echo or reverberation. The DOA system also ensures a continuous supply of 15 CFM of fresh air per person, maintaining excellent indoor air quality. Seasonal clothing insulation values, that is, CLO values, were also considered to optimize comfort across summers, monsoon, and winters. These strategies collectively help achieve 2,728 hours of thermal comfort out of 3,050 operational hours annually. Beyond classrooms, the building features pause points and walkable zones to promote movement and physical well-being throughout the day. Together, these design choices contribute to a WELL Gold rating of 62 out of 100 points, ensuring both mental and physical well-being for all users.
Our project has achieved an impressive 70% overall reduction in embodied carbon, showcasing our strong commitment to sustainable construction. This was accomplished through smart material choices and efficient design, with major carbon reductions in walls, roof, floors, fenestration, and structural systems ranging from 57% to 73%. To further lower our environmental impact, we sourced construction materials locally within an 25-kilometer radius. This, this, is not, this not only cuts down the transportation emissions, but also supported the regional economy. We used AAC blocks and concrete from Pune, ceramic tiles from Talegaon, clay tiles from Pimpri, and steel from a nearby manufacturing unit. These choices reflect a low-carbon, locally driven approach that reinforces the project's sustainability from the ground up.
With respect to affordability, our project has achieved cost optimization through smart structural and material strategies. By increasing column spans and spreading floor plates, we reduce the structural load and material use. Locally sourced materials cut down the transport costs and help reduce embodied carbon. Water demand was reduced using low flow fixtures and recycled materials like old tiles, plastic, and wood were creatively reused. Energy efficient, low maintenance systems and use of agrocrete further cut down the operational costs by 30%. A biogas plant handles organic waste and provides kitchen fuel, supporting a closed loop system. Additionally, income generating spaces like seminar hall, basketball court, and multi-purpose ground add to the project's financial sustainability. While the total cost rose from 38,305 rupees to 47,984 per square meter, this increase reflects valuable long-term sustainability features, making the project both cost-efficient and environmentally responsible.
To ensure the accessibility and inclusivity of our design, it incorporates universal design principles throughout the campus. Textured walls are placed strategically to act as tactile guides, helping all users, especially those with visual impairments, navigate the building independently. Different textures and paint colors are used to distinguish classrooms by standard, making wayfinding intuitive for all students. Ramps across the campus are designed to be truly inclusive with a gentle slope of 1:20, firm and slip resistant surfaces, and landings on both sides. Each ramp features a white color contrast stripe for enhanced visibility and safety. Together, these features create a built environment that is welcoming, navigatable, and empowering for all users of all abilities. The Super ECBC compliant school project aligns with the 8 out of the 17 UN Sustainable Development Goals, acting as a green oasis amidst the high rise urban development. It promotes sustainable practices within the community long term while offering long-term economic benefits with a return on investment in just 5 years. The project generates additional income through rentable facilities like the multipurpose hall and the sports complex. It also serves as a model net zero building for the locality. Achieving a well gold certification adds credibility, enhancing the project's environmental, social, and economic value. Our school is designed as a living classroom where students learn sustainability through daily actions. A dedicated user guide helps students efficiently navigate the building, uh, where students, teachers, and staff use the building efficiently with eco tips on saving water and electricity. QR code signages explain systems like rainwater harvesting and solar panels, which teach children about sustainability through example. Inclusive features like tactile surfaces and color-coded wayfinding aids all users, while activities like kitchen gardening and wastewater segregation encourage hands-on learning.
This is not just a school, it's a future we believe in. One where every wall teaches, every courtyard breathes, and every child grows with the planet, not against it. Thank you.
Brilliant team. You're well ahead of time. Thank you for that. Yeah, so I'll start with Saket again.
Yeah, great presentation. I really enjoyed listening to your response against each of the contest. Nice climate responsive architectural design, efficient cooling, focus on universal design access, very good work, focus on building operations, maintenance, usability, and particularly quantification of everything that you're claiming, supporting your narratives with evidence. I think overall, very good package overall. In your report, you had pushed a lot of evidence in the appendix, but now in the presentation, things are far more clearer too. So thank you. I only have one small question. You mentioned west-facing photovoltaics, right?
Yeah, so let me show you in the
concerned about that, and what is your logic? And did you do some simulation to see if it works? Yeah, this is okay. Yeah, I can see the
Yeah,
west.
so there are two roofs actually, one facing the west and one facing the south. So those two roofs were used, and those are like the monoperk solar panels, which work with even partial sunlight. So those generate electricity even in the west direction.
Yeah.
So that is why we have used it on the main roofs of the building and also on the small canopies where of the sports complex where there are sittings.
Thank you for that.
Thank you for your presentation. The praise, same as the one from Saket, very good and super interesting presentation. A lot of good axonometries, easy to follow what you've done. So thank you for that. I have a question regarding the thermal comfort. So if I understand correctly, your layout, you have the classroom in 4 different orientations. So you have northwest, southeast, like all of them. So my question is, did you look at the thermal comfort for different orientation, or did you only look at one?
We started the simulations with the critical zones, which are the west and the south. So we primarily looked at the south. So if the south was like one of the most uncomfortable areas based on the orientation. So we looked at the south classrooms and we checked that the temperatures were within IMAC range, and then we went forward with it.
Okay, and then additional question is, I think it was on your, on the slide next to this one, you showed the average temperature of a month. Like you had the comfort, yeah, exactly here.
I'm just asking, did you also consider the whole year, like hour per hour? Because here you just see a mean temperature of a month, which is not really showcasing if it's a good comfort or a bad comfort. It's a mean temperature. So maybe during the night it's good, but during the day it might be too hot. Did you also look at that?
This chart actually was made with the average of the operational hours for the month. So we kind of excluded the time where the school wasn't being used and the holidays. So from Monday to Friday, let's say 8 to 6 p.m. The average was taken from that and then put in the graph.
Okay, so for instance, in June you have like an average of 30 degree, meaning you can, if I look at June, right? Exactly. So it means it might go up to 35 at some hours and maybe 25 at some hours. So my point is just average during the day might not be the right metric to showcase it's a good comfort, because then the extreme can be way higher. So food for thought for your next design. Thank you.
Yeah, Sumit.
Thank you for the effort. I think you've touched a lot of areas beyond what the contest itself said, but necessary for good design. And I'm really impressed. A lot of things which you've done. Very happy to see that. Could you go down to the section which shows the water balance? Yeah. So, what is the kind of cooling system you've used here? Radiant cooling, right?
Radiant
And what kind of chillers have you used?
We've used water-based chillers.
Water-cooled chillers. So it's going to consume water. I don't see that on the water balance here.
So for the chiller plant, the water that we are using is again the recycled water that is going into the chiller plant, and it's completing, like it's forming a closed loop there.
Yeah.
So the reused water that we are getting from the from the taps and all the gray waters basically. So that water is being reused and then put into the chiller plant.
So you've got to have it on the water balance, and you've got to test the water balance with the number in place.
Okay.
That's something which I missed out, and think in the report also couldn't find it. But anyway, it's something for you to really think about. So this is the beauty of the contest. There's so many different sections, and if you miss in one, you're going to be caught in something else. But it is integrated design at its best, right? That's the whole idea about it. And in general, I think this has been a very nice effort. A lot of areas which you've touched. I'm very happy to see this. Thank you so much.
Thank you.
Thank you.
Thank you, team.
Yeah, did it not have a component? This didn't have a component.
Yeah, they omit to present it.
All right.
Yeah,
that was optional.
So actually, a component model was outside. You may
outside.
have seen the webcam van. It needs power, so there wasn't any power connection over here, so we
Oh,
couldn't
right.
get it inside.
We will see it later, I think.
Yeah.
Yeah.
Sure. So, folks, that was our last presentation in the Educational Building Division. Our esteemed jury panel has shown immense dedication for assessing these entries, and I want to thank them. Thank you for all the thoughtful assessment and comments. A big round of applause for them. Yeah. Also, again, I want to congratulate all the finalists. The amount of hard work they've put in, making everything, the reports and the presentation and even the competent models. So big round of applause for all of them. So as the jury coordinator for this division, I've had the opportunity to see the teams submit their deliverables. They have done some incredible work. Let's not forget that these teams have discovered a way to collaborate and do integrated design during the last 9 months. For that, I think we can give another round of applause. Yeah, thank you. So this evening, the jury members will meet and decide the winner and runner-up. So we'll decide who will it be. While we wait in anticipation, don't forget to head to our YouTube channel to vote for your favorite team. The voting is open till 5 p.m. only, so get ready to spam. Uh, we have an exhibition called the Climate Smart Innovation Exhibition, where you get to see innovative building products from the industry that addresses climate change. The exhibition is open for you from 6 p.m. onwards. So, well, it's actually open now, but the pitch is starting from 6 p.m. So there'll be 10 exhibitors pitching their products to bid to win the Climate Smart Innovation Award. Until then, have a great evening, and thank you for attending this presentation.